I'm super nervous. I'm not going to start until somebody says start.
Get started.
All right, thank you. All right. Hey, everybody, I'm Shaurya Agarwal. Let me put this in slideshow. I'm going to talk for the first 5 minutes till everybody settles, right? That way, you'll not miss this part of the talk. And I'll get the boring stuff out of the way, right? If you find me snoring or if you find somebody else snoring, none of us should be telling on each other, right? It's after lunch. It's an afternoon. It's allowed, right? First and foremost, thank you for having me. 22 years gainfully employed in this whole data, AI, machine learning thing, getting something or the other done. You can find me on LinkedIn. In fact, it would be lovely to connect with both of you on LinkedIn. Go ahead and you can't use bad words here, right? Okay. So go ahead and say whatever you like on LinkedIn. And the repo, right, again. So look for this bunch of consonants. Just random catwalk on your keyboard, my name comes up, right? And then the Silmaril, right? Can everybody hear me in the back as well? All right. I've been known to mumble, so if you don't understand what I say, or if you want me to repeat, just say so out loud. I'd be happy to do that, right? So Tacoma, thank you. I was walking yesterday along the water, and this part looks like Mad Max, and I was like, okay, we have to click a picture here. So Tacoma and SciPy, fantastic breaks. I do want to say that somehow, and I don't know how many of you come from a larger city, I come from Mumbai. And what I see happening is we are designing cities for loneliness, right? We end up, more people stay in the same area, but everybody's lonelier for some reason. We're chasing efficiency, we're chasing, freedom, individualism, something. And I feel like it's an ontology problem. I kid you not. Because we have confused community and freedom and individualism and freedom of expression. All these words, these vocabularies, we've kind of conflated their meaning, right? Why do we need a car to get everywhere? Space? Come on, right? So the concept I'm trying to drive across, look at me stutter, is vocabularies. Select a bunch of words in a given context, and that's really important. Getting the meanings right for everybody of those set of words, that's it. And if that's the one thing you take away from, how long is this thing? 4 hours? I've never studied for 4 hours in my life, I promise you. There's got to be a break here. All right, so moving on. What do you mean ontology? Somebody want to contribute? Say something, say anything. Pineapples. Say something. Groupings, that's good. Anybody else?
Classification.
Sorry, I didn't hear that. Classification, that's also good.
Relationships.
Very good. Structure. So structure, classification, groupings, relationships, we're kind of in the ballpark, right? How many of you say you've defined ontologies adequately? I'm not saying completely, adequately. None? I Googled it. Right? It says something in Greek and then something in English and then something in Latin, and I don't know. Can you define ontologies now? Somebody's got to move their heads like this or like this. Even the Indian like this is okay.
A study of being. Isn't that what what that's about.
Lovely. I don't know what that means. And my English is not terrible. This came up with Google. A set of concepts and categories in a subject area or domain that shows their properties and the relations between them. This is Latin. I don't know what this means. Anybody does? That literally is a definition found in most computer books. Not joking. So much fun, isn't it? Our language models, AI, all the next gen trillions of dollars of bubble that we're creating depends on this word, and we can't define it. So much fun. That one's even better. The branch of metaphysics dealing with the nature of being. Check that out, right? So first order of business, what does this really mean, right? Feels like you already know, doesn't it? I do. So, let me talk a little bit about myself, and let me talk about movies. Everybody's seen one, right? I work in PwC right now as a director, data and analytics, but a few years ago, right around the pandemic, I actually made a legit Bollywood movie, right? This thing won awards, this thing ran across the globe. We got called to Berlin, we got called to London, we got called to Paris. I had never seen those cities before. This thing took me places. And I made it using Python, by the way. So the project I used for the color pipeline on this thing is open source. It's called Kandinsky. It's also on my GitHub. And basically, it was made with no money. So we didn't have these fancy color grading machines. And so I had to write Python code to manage the color pipeline from camera all the way to the cinema projection. So anyways, the thing is movies, right? That's a pretty cool domain, right? When we talk about it, what kind of words do come to mind? Hey, Scorsese is a great movie director. These are toys. Nobody talks like that. But I'm just, say something. Cruise is an incredible actor, so is Hanks. Back to the Future didn't win awards. I don't know, did it?
Did that?
But it was so popular, right? Low-budget indie horror is the genre with the best returns these days. Blumhouse. Literally every movie with actors in bad lighting and horrible makeup is horror movies these days, right? Yeah. So here's how we talk about movies sometimes, right? You know what the next step is, right? How many of us have programmed in something like Java? How many liked it? Sorry. All right. Just what comes to mind, all those nouns, right? And we all kind of know the next steps here, right? Because these nouns become the classes in the classification, somebody said, right? In the classification, the structure of our ontology. We're one step closer to defining it, right? And if all I've done in, oh my God, 4 hours today is leave you with a good definition of ontology, yes, right? And then everything's kind of very straightforward from there, right? Well, how do we create a class? We say, well, what are the properties in that class? How is that class related to other classes? And we're done, right? So all the core concepts, the movie, the actor, director, you can see inheritance. Anybody remember inheritance? Yeah, so many bad nights because the inheritance was messed up. Oh my God. Yeah, I was younger, my hair were black back then. But yeah, the actors and directors are both persons, right? A character is a fictional or a real role portrayed in the movie, and a genre right? We talked about horror, right? I'm really nervous, and I'm talking about horror pictures. Just excuse me for making any gaps here. Okay, and way we look at is data properties. First and foremost, what defines that word by itself? What defines a movie by itself? A movie has a title. A movie has a release year. A movie has some duration. A movie may have a rating, right? An IMDb rating, or some sort of a rating scale, right? Rotten Tomatoes, whatever, right? Similarly, a person will have a name and will have a birth date. A character will have a name, right? And a genre, of course, has a name. Ideally, a genre would also have a description, but anybody want to volunteer what's the problem with description?
Subjective.
Subjective, thank you. So we can't agree on it. And so we'll have something like that on the ontology. 10 years later, when the bridge falls down because the engineering was not right, we'll say, oh, that one property was just subjective. We didn't agree on it, right? So we have to, when we're doing ontology engineering, chase down subjectivity and try to resolve it into objective parameters, right? Which means we can't write poetry in ontologies. But hey. And then relationships. Has actor. That's a relationship between a movie and a person, right? For the database people, everybody would have used a database someday, right? If nothing else, SQLite. That's a foreign key relationship. Make sense? Too much? Too boring? All right. Has director, the relationship between a movie and a person again, right? Plays a character. Indicates when an actor played a character, right? Yeah. All of us have done this, right? Right? So, I don't know how much time has passed, somebody keep telling me, but whatever, a few minutes into the session, can we now try and define ontologies again? Do you want to volunteer again? We all know we know. We all know we know. And it's no longer the Greek and Latin we saw earlier. So give me a chance. Once more.
Nouns and their verbs.
Thank you. Yes. Right? So we're looking at nouns and verbs, right? Properties and classes, right? Taxonomies. But are we there yet? Like, why use ontology when we had object-oriented programming and we had like so many books and like 5,000 consultants telling us how to make a class structure? Then, why did we need the word ontologies? And by the way, ontologies, when did they become popular? The guy who invented the internet, or I think I'm told he did, Tim Berners-Lee, he used the word ontologies. So, yeah, there's meaning behind the word. So we just built an ontology, did we not? Like it took us maybe 30 seconds and we built one, and we still can't define. That's fun, right? So these are the two words. At the start, when I was talking about Tacoma, I talked about vocabularies, being really specific about each word, right? The other word that is very important for us is declarative. As you can see, I do not know how to write on paper properly, so the words are anywhere and everywhere. But if you have trouble reading, just let me know, right? Declarative and vocabularies. We're getting 1 inch closer to the definition. declarative is not imperative. Everybody knows what declarative is, right? Declarative programming, right? I'll give you examples. And vocabularies, right? So, that PhD thing, let me tell you about that. My dad was a professor at this college called IIT. It's one of those prestigious colleges in India. So he did all the studying, and I never studied, right? Because rebel, right? But when he used to guide PhDs, he used to ask these two questions, right? What's the ontology, and what's the epistemology? Somebody pronounce that for me, please. Epistemology. Epistemology, right. Yeah, good. We had one word we couldn't define, now we have two words we could define. Turns out, and he explained this to me really well, knowing about knowing, or how do we know something? How do we know that bacteria cause disease? How do we know running faster burns more energy? How do we know something is the epistemology. Woody Allen has a lot of jokes about that. Ontology is what do we know about it? What bacteria causes what disease? Right? What amount of energy is burned when you're running at 5 miles an hour? Right? So that's where we're in. What, not how. When we say what, we're talking about declarative, and when we're talking about how, we're talking about imperative, right? So when you write a database query, you say select star from employees table. You don't actually say how to go locate the database table on the hard drive, or where in the network that hard drive is located. You don't explain to it when you say order by ascending. You don't tell the database which sorting algorithm to use. You just say what you want. When you're in a restaurant and you say, I want chicken pot pie, you don't go and explain how to make that dish. You just say, hey, there's this vocabulary that you and I both agree on. We both know what chicken pot pie really looks like and is, and everything. And hey, I want a chicken pot pie. There's an exchange of vocabulary. Meanings are really well understood. The how is taken care by like people in white hats, right? So when we separate the what and the how, the what part is ontology. I kid you not, it was like 4 characters. Why did they use so many letters in it? They could have just said what, right? And you could do what with groupings, you could do what with classification, you could do what with structure, you could do what with nouns and verbs. What is ontologies? Right? I'm going to play with this concept for the next 4 hours, oh my God. Okay, so I blame the name. This is a branding problem. Look, I'm an engineer. I don't understand marketing, but seems like an obvious thing to me. Why did they call it ontologies, right? They could have, like, if you go science fiction, we could have said, or fantasy, we could have said, hey, Harry Potter had that Marauders map. It's kind of simple, right? Why couldn't we use it? Why couldn't we use that name? Well, it's not cool enough, right? Douglas Adams. How many people have read Douglas Adams? Okay. You guys are my favorite. Just Hitchhiker's Guide to the Galaxy. That's a good name. I like it. Right? But too long. Too long. We're trying to reach what? Right? And then what happened was I, in PwC, was working on Palantir Foundry, right? And when I entered, I had only heard the stories and I'd never seen the application myself. And now that I have built and delivered so many different use cases on it, I know. And so my first question was, what's Palantir? And they said, Lord of the Rings. I said, okay. So how about calling the ontologies the Silmaril? Not bad. Closer, at least a few characters less. It's not what, but it's something. Right? So we discussed the vocabulary, right? Clearly state the concept. Clearly, in one world, one word means one concept. Which means if you have something like a name in an employee's table and a name in a customer's table, you can't have that. You're going to have employee name and customer name. You're going to have two words. Specific thing for a specific reason for a specific meaning. Right? And when we're running code, and hopefully everybody's awake when we get there, we'll actually see those errors occur. Right? And so with this specificity, you can imagine when we actually run things, we can automate a lot of the grunt work, right? And declarative, right? We talked about SQL. In Pandas, right, you just say, hey, filter this thing. You don't care what the algorithm is inside. You actually don't care. You have to these days a little bit, but you don't care if it's running on Arrow or if it's running on its native implementation or if it's vectorized or if it's not. It's making us scared these days a little bit, but that's the how. You can just say, hey, filter this, and it filters it for you, right? Or join two tables. It doesn't say go match these two string values and where the values match, do this and do that. No, you just say join, left join, right join, whatever, right? So separating the what and the how helps. I should have written sometimes here. I didn't. Sorry. So a lot of logic and reasoning right now becomes imperative when we're looking at object-oriented programming, when we're looking at database design, right? In a database, how many of us have struggled with representing a tree, a parent-child relationship within the same table, right? You're going to have a primary key, and then you're going to have a parent key right next to it, and the parent key is going to be a primary key within the same table. So good luck making 10 self-joins before you get some meaning out of that table, right? Has somebody cracked that problem ever? In a retail situation, you have departments, and in you have a big retail store, you have departments. Departments have aisles. Aisles have products in them. That's a hierarchy, right? And in your inventory table, you're going to have a primary key, and then you're going to have a parent ID within the same thing. Or you're going to have a multitude of tables, right? So what's happening is you have to necessarily think about the how when you have to reason about your inventory. We want to separate that, and ontologies lets us do that, right? A little bit more comparison. Right? Because, we can't understand what a horse is unless we compare it to every other animal that we know about, right? So all these things, somebody did use the word taxonomies earlier, right? Right, somebody did. All right. Right. Can anybody explain the first one to me? Abstract syntax trees? No?
Typically, when you make a language, you want it in a more compact and easy to parse representation. So you take all the main kind of features of your language and break it down into a non-cyclical tree, and then you can use that to generate the next level of representation.
Perfect. Yeah, exactly. So when we speak a sentence, right, how you understand that sentence, what's the subject, predicate, object, whatever, right? In our mind, we create a tree of meaning, right? Abstract syntax tree. Wherever we define syntax, we define it using a tree structure. That's what this is. We are not good, fun. We don't know how to create good names, seriously. Homework. Can we find a more cool name for abstract syntax trees? You see that and it feels like calculus exam tomorrow. No. Anyways, taxonomies. Everybody's seen taxonomies, right? What's the most commonplace? Table of contents. That's a taxonomy, right? In the biology classes, I used to have these genomes and the animals belonging to that genome and all that, right? So that's a taxonomy. Thesaurus. Everybody knows what thesaurus is. Everybody does. Come on.
Similar words to like what you...
Similar words, yeah. Synonyms and antonyms. Ontologies, we just talked about. Knowledge graph is when ontologies have data in them. Right? Palantir people call it hydrating an ontology. Good. So, syntactic structure without any meaning, just pure grammar. Right? The stuff that puts us to sleep. That stuff. Right? Taxonomies is simple semantic organization. You know? Here's the flow of the chapters in the book. Here's the flow of the events in a story. Taxonomies. Thesaurus is a taxonomy, but with all the synonyms and antonyms in the terms. Right? Ontologies are now richer semantics. It's going to say, here's the rules, here's the restrictions. We saw the rules and restrictions. A movie has an actor, a director is a person, an actor has acted in a movie or something, right? So all those relationships and the rules and restrictions, that was ontologies. And knowledge graph is just, think about these as the classes in object-oriented programming, and the knowledge graph is the object, the instances, when you add actual data to it, right? So for 30 seconds, just going back to that slide, right? We don't actually have a real movie here, right? But if we said movie, title, Back to the Future, person, actor, Michael Fox, character, what was this character? I don't remember. Whatever. Sorry? Marty McFly, of course, yeah. And genre, science fiction or fantasy, whatever, right? Then that one thing becomes a knowledge graph. This is the blueprint, that's the building, right? An instance is a knowledge graph. The specification of that instance is an ontology. How simple is that, right? We knew ontologies all along. So I'm going to rush through this thing again, and here we are, right? We can do a little better. Let's dive one level deeper. I'm going to test you guys, right? Don't fall asleep. 30 seconds. Right? Let's look at a little more detail, right? So what's the structure look like? An abstract syntax tree is a tree, right? But then we can, connect different nodes with if-else relationships, and it's not just a plain tree anymore, it's a more rich graph, right? So ontology onwards, everything's a graph, right? I don't know why I said hierarchy in taxonomies. Taxonomies are also trees, right? The focus is syntax, semantics, and taxonomies we only use for classification. When we talk about knowledge engineering, limited to classification. If you're using taxonomies for something else, we have used it for something else sometimes. Breadcrumbs in a website are used for navigation, right? But breadcrumbs are also helping us classify the website in our heads, right? So prefer just classification. And the relationships are, that's the most interesting part, multiple semantics. This gets us closer to how our language works, right? Knowledge representation then is the most important thing these days, right? And yeah, flexibility, I don't really think, it's fairly straightforward. So taxonomies and ontologies we saw provide schema, whereas knowledge graphs populate the schema with actual data, right? So So for now, we now know how to define ontologies. Somebody want to help me? Define an ontology for me. It's one word. Come on. What? Thank you. Right? We now know how ontologies get hydrated. And when hydrated, what do they become? Knowledge graphs, right? And so yeah, we know ontologies, we know knowledge graphs, we're done, right? Let's take a couple of really, really simple analogies. I don't think they're perfect. I was very tired yesterday night. I wrote the slide yesterday night. So if anything, try to find fault here, okay? But like, I think everybody understood this one. That was the basis of this analogy for me. Like the Dewey Decimal System is nothing but a taxonomy, right? And then ontology is like a detailed catalog, right? So when you expand an ontology, you can even add the index of terms behind every book. You can just add that into the data structure as well. You just have to make sure that the terms are unique across the board, right? And then knowledge graph is literally the library. Make sense? If this is taking us back to confusion, just close your eyes, all right? City, right? Abstract syntax tree is your addresses, right? Taxonomy is how we organize a city, right? Ontology is literally everything else, making the city, make sense, right? We can say that there are 3 districts, but when we come to the ontology, we say this is the arts district, this is the manufacturing district, and so on and so forth. This part's going to have an art museum, and the other part's going to look like Mad Max, and so on. Like in the knowledge graph is actually the city itself then. Make sense? I promise the theory is going to be over in like 2 seconds, and we'll start working through code. Oh, it is. Oh, I thought there was another slide. I'm sorry. All right. Yeah, so for those of you who've not seen this yet, the repo also has this list. Please go ahead and install some of these. And if you've already installed, we can just start. Begin?
Maybe installing the Jupyter notebook environment.
I have the commands over there, so you use an exclamation mark. If you want to fire a bash thing, you just use an exclamation mark. Right. Everything, all my mistakes and all the good points, everything's open. Right. And what I'll do next is just walk you through the GitHub repo once so that it stays open. And all of you help me enrich that as well. Right. So moving to the GitHub. Did I kill it? Yeah, this is the repo. I'm sorry.
I think there are a few more like PySpark and Baker that I found.
Oh yeah, they are. We're not going to use them for the workshop. They're there in the repo, and the repo is going to have like a lot of requirements because there is a very diverse set of ontologies that we're building there, right? But we're not using them for the workshop. You should be fine today. Okay. This is the GitHub repo, right? What I've done is I've tried to organize all the ontologies that I was building, and this has grown organically over the past few months, as and when I would see some use case, while I'm traveling, or I'm talking to my colleagues, or I'm talking to friends, customers, whoever. When I see a use case, I try to isolate the.
What?
Yeah, thank you. That's actually the right answer. And he asked it with a question mark, which is even better. So I try to isolate the verbs and the nouns, right? I try to isolate the what. And that what, so the way this started was I wanted to capture the what and then say, did I do it right, yes or no? Right, just go back 2 days, 2 weeks, 2 months later and verify. Some of them stood the test of time, others are, oh my God, blunders. Right, just close your eyes when you see them. When you click on that folder, just close your eyes. We'll consider, I think, probably the first 4, because I think we'll run out of time beyond that. But I think I have added ontologies all the way to all of them. Like there's 25 of them. Let me click on anything random. There's got to be an ontology here. Yeah, there is, right? So there's this structure file that's going to actually inform the ontology, right? So that, right? So literally every folder is going to have some version of this thing, right? I tried to make the boxes colorful. I'm not good at mermaid, so somebody help me. All right, so I'll go back to Silmaril. I have opened the discussions page here. What I would really appreciate, because, 4 hours, even though someone like me, for me it's like half my lifetime, I don't think that's enough time for all of us to ask all the questions that will come to us. So let's ask them here, because the more questions we ask, the more words we get, the better ontologies we get to, right? So we'll start with movies and music. We're going to spend a considerable amount of time on, and then I've added some more features in the supply chain part, and then even more features in the insurance part. So we will see a progression, right? For each ontology, we're going to start with first building the ontology itself, right? And we'll explore a couple of formats in which we can do that. And then we're actually going to try and use the data and the ontology we've written to reason about, and that's the coolest part, right? My hope slash suspicion is that right when you're about to fall asleep is when you'll realize the value of ontologies. So don't rush it, right? It's that moment when you're like, oh, that's what it does, right? So I'm going to get to that in the music part, just laying it out there, right? The other part is that these links are all broken, because what I did in my excitement was I went ahead and renamed all the folders, so they now represent the ontologies that they contain. Earlier they were just 01, 02, 03, 04, right? I just renamed the folder, so all the links are broken, so congratulations, but you can click on the folder so it works. But all the references that I used are here, literally everything. Like if there's one remote YouTube video that I listened to but I should have seen but I was jogging or something, I have even listed that, right? Everything's here, right? If you find more links, go ahead and change it, right? Go ahead and add to it, right? The best part here is when all of us get to use this resource, because, believe it or not, ontologies were cool exactly 20 years ago, actually. That's, seriously. iPhone had not been invented then. They thought, all right, we have the internet. What if we could link all the pages and extract not just the text, but the meanings between the pages? That was the glorious mission, right? For which they started using it. And some of the ontologies that we use today actually survived from those days. Yeah, I think Tim Berners-Lee came up with the first properly working reasoning engine, and guess which language it was written in? Python. 2003, the first time we're able to reason about the web, the World Wide Web, we were using Python. It was that cool, right? So that project on GitHub is still there. I don't think it's been updated for like 15 years. So pick it up. I have a link here. Pick it up, modernize it, go play with it. It's so much fun. And it's because we will be building our own reasoner, we will be doing a little bit of what Tim Berners-Lee did, right, today in these 4 hours. You should be able to pick it up. There's no reason why you can't modernize it, right? So the link to that is somewhere here. Yeah, there we go, CWM, the closed world machine, right? By the way, open world, closed world, the only two lawyerly terms, and I'll never talk about them ever again, but just so we know, right? In Bollywood movies, there's this joke that, this staircase goes from the bottom to the top, but prove that the same staircase comes back from the top to the bottom, right? That's a closed world assumption, which means the facts that are not stated, we don't know anything about them. Open world, we know, yeah, we can make assumptions. Closed world, unless and until we have stated something very clearly, right? Well, a very good use is a parent-child relationship, right? A parent has two children, but unless explicitly stated, we cannot assume they're siblings in a closed world. In an open world, go ahead. Right? So there's two ways to reason about ontologies, closed world and open world. Right? Guess which one is easier to automate? Closed world. We assume nothing except what's been told to us. Right? And that's why Tim Beale said, okay, I'm going to make the closed world machine. And literally all it does is, hey, this thing is related to this thing, so this thing flows from here to here. That's it, right? Movie has an actor, actor is a person, movie has a director, director is a person, movie has an award, so on and so forth, right? Straightforward stuff. We don't assume anything else about the movie. The movie has a poster. We were never told that happened, right? So yeah, so do you guys want to check it out? Look at that, 21 years ago. That's incredible. I don't know if there was GitHub 21 years ago, but somehow, like it's whatever this is. I'm trying to locally use TLA, so this will get hopefully this comes from CVS, guys, CVS. How many of us have used CVS? Okay. True story, I tried using it in college. I failed that class. And I was a good programmer. So I am a good programmer, come on. Was. Yeah, so CVS was that clunky. And then SVN, when SVN came in, I was like, all right, yeah, somebody figured it out. And then Bazaar and Mercurial, and then finally Git came in, and we're happier now. And we have better things down the pipeline. But that's a different talk. Git's where it's at because it's the most popular one right now. But yeah, check this out. This is pretty cool. There is a CWM folder here somewhere. Really? Oh, there we go. That's it. That's all of it. This literally is the first reasoner on ontologies that the planet saw properly working. The guy who was, I think, instrumental in building the internet built this one. Pretty cool, right? If nothing else, we can like take a printout and say, I have a piece of history with me, right? So, come on. So two things we carry away: the definition of ontologies and a printout of this code. Come on. Already gold, right? 4 hours. Okay. So the next thing I want to do is open up Jupyter Notebook, and I want to try building the first ontology here. My God, I'm a big fan of this word right now. Can everybody see this? All right. If you go to GitHub, I don't know where this is. Oh, this is in the movies. Start at number 1, basically. So in movies, we have building our first ontology, N3. All right, so we're going to start with a way of expressing ontologies, which are like really, really, really straightforward, because we want to look at the what, and then I'm going to take you into N3. All right, which is the first slightly richer way of expressing ontologies. In fact, N3 is my favorite way, right? Everything else is clunkier than that. So the first thing we do is look at the structure here, okay? When I open that structure file, and it's really simple. I just kind of used like a YAML-like format, just pure pseudocode type stuff. So you can look at all the classes. So there's a class called movie. Movies has data properties and object properties. Do you remember what data properties were and what object properties were? Somebody. Data properties were? Go ahead.
Like attributes of the nodes.
Yeah, defining what that thing specifically is. Data properties. What are object properties?
I guess it's less of a definition, but I do have a question about them.
Sure, yeah.
So like when you look at something like this, that has director, has actor, it seems like a lot of the semantics that are embedded within this property could also just be deferred by like what node it is connected to.
Yeah, exactly.
To an actor node, like isn't it kind of also just like a
Yeah.
as actor?
Yeah.
So I guess when you're building out ontologies like this, how do you balance kind of this like specificity with your properties versus kind of the more generalized composability that one might have?
Right. So the question is, how do we, looking at these properties that are object properties, and he kind of answered the question as well. Object properties are relationships. They're links between two objects. And when you think about it, we're talking semantics, right? We're talking like building a semantic web or a graph. So there can be different types of links. There has to be different types of links. So just because we have all three links here put in one place doesn't mean that they're like the same link. The has actor database is a join between actors and movies. The has director database is a join between directors and movies. So all your joins in a database are the links, and each join is effectively a different link type. Did that answer your question? So we're saying I used to have types, string, integer, float, or a complex type, which is a class, movie, and I'm going to say, hey, even my link is a type of data. Well, every link is a different type of data. Yeah, go ahead.
So if I'm following correctly, then you could have another class that's a TV show, right?
Perfect.
You could also have an actor and a director.
Perfect, yeah.
So then what's like this is a stupid question, but like the Pythonic way of creating these classes? If you wanted to create a movie class and a TV show class, do you define actor separately within both? I mean, probably not if they have identical properties. So where does the definition of the actor property go? Since I assume you wouldn't want it within each of those classes.
Right. So the question is, if in this ontology, along with movies, we had this concept of a TV show, fantastic question, by the way, how would you then have unique relationships? Because even the TV show is going to have a has actor and a has director, right? So the first thing we need in that case, just like actors and directors have a parent called person, so we're going to have a mass like a parent, right? That parent will have a has actor, has director. So when movies and TV shows inherit from that parent, we still have uniqueness. Or the other way around is we're going to have to like break every single of these relationships, and we're going to say has TV actor, has movie actor, has TV director, has movie director. So one way is to explode all the properties, and the other way is to consolidate the hierarchy. Both works, and in my experience, we have to keep an open mind. Because I promise you, the movies and the music ontologies are solved problems. Problems happen when your company acquires a new supply chain company, and that company has AS400 servers that were run by a person who just retired yesterday and has moved to Mexico, right? That's the problem. So that's when you have to keep an open mind and say, wait, I'm not here to prune the columns, and I'm not here to make an elegant tree. Maybe let's just explode the properties and take advantage of, high compute facilities here. We'll use a GPU this time, right? So that sort of stuff. But fantastic question. Thank you for that. Any other questions before we kind of scroll down? Yes, sir. Please go ahead.
How are we limiting ourselves? Are we limiting ourselves in the extent to which we can form relationships? So like, I don't know how I can do this in movies, but like if you have a noun like manager and another noun like employee, manager manages employees but also is an employee. So you have two separate relationships from one node to the other node.
Right.
Is that?
Yeah, perfect. That's a brilliant question, and we'll see some of that. We'll see we have a song, and then we have a rock song, and we have an album and a rock album, and it's not exactly the same that you asked, but let me repeat the question. He said, well, how are we sort of managing all these relationships when you think about a case where you have a manager and an employee, right? So an employee is going to have a has manager, and a manager is going to have a manages employee relationship, right? But a manager is also an employee. Fun stuff, right? So this is where we're crossing sort of wires with knowledge graphs, right? What we'll do is we will, in the ontology, have these relationships, these link types, and we'll have to think through these things when we hydrate the ontology, right? We will do some of these exercises down the road, right? But I want to start here and then move on to N3 real quick, right? Right, so this is pretty much straightforward, right? We don't have anything else in a director, which is like everything in a person got captured here, and that's it. So I divorced the how and the what in my head as well. And I said, I don't want to learn how to write N3 or RDF or OWL, or I don't want to know how to express an ontology. Let me just express my ontology in the simplest way possible. This is extremely limiting, as we'll see in a minute. But it gets me interested a little bit, right? Right? So what I would request is that you just like copy paste this in a notepad somewhere so we can refer to it when we're building the N3, right? Somebody give me a signal and we'll start the N3. We're getting to code now. Good. I'm going to justify the 4 hours now. Okay. Should we? Good? Okay. So I have it in the Jupyter notebook opened up. What I would expect you're doing while I'm walking through this file is you're building the N3 in a plain notepad VS Code type situation. right? The solution to this is right here. So I have a movies.n3. All right, let me open that in code and show you. Right, so hopefully as I'm walking through the Jupyter notebook, you're building this in parallel. All right, build it, because we'll make a mistake or we'll figure out a new relationship, and that's going to be very interesting for everybody. All right. There was something else I wanted to say and I forgot. Yeah, anybody know how to increase the font size in VS Code? Sure? No. Oh, come on, I don't know why we go to Control Plus for anything.
Control comma, I think, is the setting.
Appearance, editor layout. I'm not going to waste time on this one. You're using code, I'm using Jupyter. The Jupyter font sizes are set for me. So, all right, let's move forward. We only have 4 hours, all right? Okay, the what, right? So we isolated the classes. This is like we're doing it for the 3rd time now. What are the relationships, the verbs, and what are the literals, the data properties, right? And what are the constraints? Right, this thing, I don't know, there was a movie where Kate Blanchett played a rock star. Like Bob Dylan was played by like four actors in that movie. Yeah, so Kate Blanchett also played him. So I like her performance there, but what I'm saying is that this is like a made-up relationship. It's going to get broken down the road, right? But this is our what. This is a general purpose sort of rudiment of the what. Okay? Now onwards, we're getting into the how, the N3 technology. N3 stands for notation 3, right? Somebody has to tell me what notations 1 and 2 were, right? This is like C. There was a language called A and a language called B, but we only know about a language called C. Similarly, we know notation 3. I don't know notation 1 and 2. Did I open the wrong notebook? Give me a second. Yeah, okay. So the concepts are fairly straightforward, right? Classes, object properties, data properties, restrictions, inverse properties. Employee has manager, manager manages employee, right? The stairs go from down to up, and the same stairs come from up to down. So we express both because we're in a closed world relationship, right? If we don't express the inverse relationship, we can't assume that, right? So inverse properties and rules. In fact, one of the first things we'll see in maybe 20 minutes is how to calculate these inverse properties. And you'll realize that's the first aha moment when we'll go, oh, ontologies are cool, because computing inverse properties in a database, it actually doesn't happen. You have to create a database view, and somebody has to manage that view, and while that view is being created or computed, our salaries don't get credited that day, right? Because Oracle's slow, or something like that happens, right? So inverse properties in RDBMS, hard. In Java, slightly easier, but still hard. Here, it's default. It's automatic, right? This is just a sample. Right? This is just a sample. I'm going to have to read from my screen because, you know. So the notation 3 format. First, we're going to say prefix. Prefix is just like the import statements at the top of your Python code. Right? We say import OS. That means it's going to bring in all the nouns and the verbs that the OS library has. Right? Import date time, that means now my code has the capabilities of modifying or manipulating date time data, right? Because all the nouns and verbs from the date time module came into my code, right? So that's managed by prefix. Now, it's intuitive, although ugly. I had all the variables in the world that I have seen and that I'm yet to see, how will I name them in a unique manner? What's the one scheme we know works every time? If I had to name every website that I've seen and I'm yet to see, how will I uniquely name every single website? I will create what is called a URL, a universal resource locator. Right? The problem with the URLs was they only work in English. You can't have like an accented E. I think you can now, but you still can't. And so, universal resource locator graduated to being used as universal resource indicator. It's not exactly a website, it points to something in the network, right? And then the prefixes use something better called the IRIs. I always forget if the I is international or something, I don't know.
From universal to international, that seems like a downgrade.
Yeah, it does. The only thing is that IRIs actually support all of Unicode. So you can write IRI in any language. You can write it in an emoji, just full of emojis, and it'll work. A URL, I don't think you have like a give me a set of emojis, right? And .com, that's not going to happen, right? So these things are predefined vocabularies. These vocabularies are now giving us an idea of, hey, there are these agreed nouns and verbs we use in the definition of an ontology. Remember, ontology itself is a word, right? Which means we need definitions for that, which means it's going to have data properties, it's going to have object properties, it's going to have rules and restrictions, right? It's a word. So where are the definitions of that word? They live in these three definitions, not XSD. In OWL, in RDS and RDF and RDFS, right? This is typically how we do it. Like you can use your own domain name, right? But when we're just playing with ontology, we just use example.org. It's more convention than common sense, right? Because I'm pretty sure somebody has purchased example.org and it's going to sue us any day soon. But yeah, so how do we define any fact? We say it's a triple. Right? Noun, verb, and a joining verb, right? So movie is, we just skipped the word is. This is the convention, how you write N3. Movie is a class, right? And its label, its name, its friendly name is movie. Did that make sense? This is a triple. This is a connection between movie and the idea of a class. Make sense? This is really nuanced, but if you just get past this point, we are going to be building nuclear reactors in 30 seconds, right? Just this past this point, all right? So the most nuanced, and this is where I've had the most amount of fun as well. Right? Sitting with a bank and working out the invoices. Oh my God, you have to make them think. And you have to keep questioning. It's almost as much fun as building a new product. Because you have to understand how people are thinking about their day-to-day work. You have to bring out the hidden stuff. So here we're saying a very simple thing. Movie is a class, which we said above as well, right? We said that here. Things, right? Movie is a thing. Movie is a class, right? We said that. And so we're saying that here as well. And then here's how we define a property, right? Directed by is a property, object property, right? Its domain is movie, its range, it's related to a director. From, to. Domain, range. One of these guys was like a math grad. He wanted to flex, or she wanted to flex, I don't know. It's probably a he, like women are more intelligent emotionally, in my opinion. I'm turning into an old sexist idiot, but it's probably a he. Domain and range could be from and to. We should be using simpler words. There's this, Hemingway told us we have to use simpler words, or it's not genuine, it's not authentic. But they don't use it, I don't know. They want to say ontologies and domains and ranges, and they want to pretend that they're smart. My rant over. Here's all the classes that we've now defined. A movie is a class. Its common name is whatever that movie is, right? So when a computer is printing the results, it will print this thing, right? When a computer's logically connecting the variables, it's going to use this thing, right? So even in code, we have the address and the variable name, right? We have the memory address and the variable name. So this is the pointer, this is the friendly name. Make sense? In databases, we have the primary key and the friendly name, or the title sometimes, right? Is that. So now we can define key properties. Similarly, we have directed by, there's a domain, there's a range, and there's a label. We have actor, acted in, we have title, we have release date. Have we been able to code that so far? Here's how this is working in code. We declare our ontology, and we have a movie is a class, its label is movie. A class doesn't have a domain or a range, right? And so we define all the classes, and we say the subclass of property is used to define parent-child relationships, inheritance. Make sense? It's boring, I know. Just stay with me. Right? Okay. And then the data properties. Properties have domain and ranges. Properties say, this is where I belong, and this is what I impact. Right? To and from. And then we have the link types. So let me get to the link type. We have object properties. Right? So this is actually not convention, this is just a comment, right? We're actually using domain range here as well. It's literally a property. Make sense? Okay. Confusing? Should I wait? Do you want to type a few of these? Okay.
So
Sorry, go ahead.
You defined movie to be a class, but then it's a subclass of.
Where are you saying movies a subclass of?
Maybe actor. But you have actor is our class, and then also actor is a subclass
Of person.
Of a restriction.
No. So if you look at this screen, person is the superclass, right? And then actor, line number 26. Actor is a subclass of person.
But then above you have also actor as in our class.
Yeah, actor is a class, which is a subclass of person. That's how you would do inheritance, right?
Okay. Gotcha. Thank you.
Right? So I have a question for all of you, right? Subclass of. Is that a data property, an object property? Where is that word coming from?
I was going to say data property.
Anybody else want to take a crack at it? It's fun, come on.
Could it be either?
Really? Okay, that's, yeah. Anybody else? Give me a reason. I know you know the answer. I can see it in your eyes that you know the answer. Just say it out loud. He says object properties. It's a data property. It's not relating anything outside. It's literally just inheritance. But she's right that if I was to change my context and if I was to start looking at relationships only, this thing becomes an object property. So context, right? But the subclass of word, this vocabulary that we created is standard, right? When we're defining N3, we need words to define our ontology. This word was defined inside an ontology called RDFS. Right, so before I could start defining my ontology, somebody had to define an ontology to say, here's how you define an ontology. Make sense? And that's where we had to bring in all these things, right? So if I am, and we'll see in due time, if I'm reasoning about time, I'm going to have to bring in something that talks about time. If I'm reasoning about some other data structure, which is kind of a standard, then math, for example, then I have to bring something in that has the vocabularies for math, right? And so on and so forth, which is just like programming. You do not go and implement square root from scratch. You just say import math and then you go SQRT, right? So everybody's using the same method name. So it's just that it just looks a little hard to read because we're not used to, right? And when Notation 3 was built, XML was the best format we had. So we can obviously do better today. We can build a smarter format today that's more readable, right? This thing, like I showed you, is 21 years old. We can do better. Come on. We don't need so many colons, and that's not Pythonic, right? So we could definitely make it a little more readable, but this is what we have right now, right? In fact, fun fact, although today, with Palantir and so many other companies, ontologies are extremely popular, extremely important, and cost billions of dollars. The last ontology reasoner was built like 10 years ago. I'm not joking. We don't have open ontology reasoners available today. I found this fantastic research paper, which would be there somewhere. You guys love tangents, don't you? No? Come on. It confuses everybody, which means wakes people up, right? There's got to be somewhere I have put. Yeah. See, this is a research paper that says OWL reasoner still usable in 2023. Some poor soul actually did that. And imagine, and this gentleman has then, gentleman? Yeah, I don't know. Has then created this really nice list which says abandoned, 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 abandoned. These were like all amazing projects back in the day, right? And the one that I like the most is called Reasonable, and the other one that I really like, is called EYE. I has something to do with Euler. I don't know why they called it I. EYE has nothing to do with reason or ontology, so I don't know why they called it, but like it had something to do with Euler. Yeah, I don't know where reasoner is. But this is all we have. I'm not joking. Spark, NetworkX, Apache Spark uses ontological reasoning. Your Google webmaster site analytics use ontological reasoning. There's an ontology called friend of a friend, FOF. It's still used on the internet today. Not even joking, just FOAF. Put that in your bar, Google bar, and you'll see that, right? But the last reasoner we had was like 10 years ago. It's incredibly annoying. We can do better.
What do you mean by reasoner? Like what? Is it like a
So-
compiler or a parser?
Yeah, thank you for asking that. So we just defined a bunch of these, let me go back to the Jupyter notebook. We just defined a bunch of these relationships, right? Now I should be able to say a movie, when I add in my movie database, I say movie Jurassic Park directed by Steven Spielberg. You should now, the query should be able to reason and say all the movies directed by Steven Spielberg, right? The inverse relationship. So the reasoner, once you define the rules for the reasoner, will be able to infer any future data that is added or removed from your data set. We'll actually see that. We'll see that in action, right? So all these properties, I guess the point I was making, and I'm lost completely, and my knees are shaking, to be very honest, is the way we talk about an ontology is defined by ontologies, and the three main ontologies that help us do that are RDF, Resource Description Framework, RDFS, Resource Description Framework Schema. We're not good with names. Remember, this domain, even though they're talking about words, they're like really horrible with names. Oh my God, right? Like the most boring ones, abstract syntax tree. Aaron Sorkin would be very happy with these names. Lots of dialogue. I mean, like, right? So anyways, so here we have now defined basically our movie ontology in N3, in notation 3, using formal vocabularies provided by standards, right? Now, can we add inverse properties? We will never have to enter the data for inverse properties because the reasoner will pick up these inverse properties and automatically add this data into the database. Go ahead, sir.
Sorry, can you cover domain versus range again?
Do you mind saying that again?
Domain versus range. Could you cover that one more time?
Yes, we had it here. Domain range. So your data and your data and object properties have domains and ranges, from and to. The inverse properties.
So why in your example with domain, let's say directed by domain is movie, acted in range is movie? But to me that's the same. Is that because of the range?
Do you want to point to which example you're talking about?
It's like properties directed by owl, property, domain movie, range director.
Right. So imagine a database table where you had basically a movie, and you'd have the title, you'd have the director, and so on and so forth, right? So we're doing that same thing, but in a semantic manner. So let me give you a glimpse of the data that we have. Right. So we can actually go into the movie CSV, and I'm going to open it in Notepad++. Right, and see it has a director ID. Do you see that? Right, so it's going to have like some director named somewhere. Right, that's the ID. So in a RDBMS, and we're used to it, but it's not really easy to understand for somebody who's first seeing the RDBMS. Relational databases are like a mess. I don't know if anybody here can tell me the difference between second normal form and third normal form? Or why even care about it? How many of us actually use second normal form? We don't. We use flat files in third normal form, right? So the thing is that databases, so what I'm trying to arrive at is that this is how you would do it in a relational database, right? But it would, in a ontology, and let me get to that property. You're talking about, I don't know where did it go? Oh, this one. So you're talking about directed by, right?
Yeah.
So you're trying to understand that block?
I'm trying to figure out why movie is flipped on domain versus range between directed by and activated. Because to me, the director and actor are both more or less the same relationship to movies, so I would expect.
You're saying that it should be the other way around. So you're saying that the domain should be directors and the range should be movies, because a director directs a movie.
Yes.
Yeah, I think you're right, yeah. Yeah.
Could I try to,
Go ahead.
if you were to draw like director in a circle and then movie in a circle, and you draw an arrow from one to another, you would draw an arrow from director to movie and label that director by, right?
I think I would do the opposite.
Okay.
Yeah, so we can look at it. We can look at
Fair
it.
enough, fair enough.
So we can look at it. So the arrow that I drew in my the ontology structure was from the movie to a director. A movie has one or more directors. That was the cardinality in my head. Right, because remember, when I wrote the ontology, I was just trying to write the ontology and not worry about N3 at all. Right, so thank you for bringing that point up, because this is where we have to, just engineer the ontology correctly so the semantics work. Right now, what you're looking is a hack job because somebody was too lazy to study N3 before writing the first ontology. Right? Yes, go ahead, sir.
Both directions here.
It can be a bidirectional relationship, you're absolutely right. And we'll see bidirectional relationships in literally 2 more ontologies from now. Yeah, go ahead, sir.
I think the original hang-up was because when we're talking about director, the movie's the domain, so when we talk about the actor, the movie's the range. I think he was pointing out that they should be consistent, where either the movie's just the domain or the movie.
I agree. No, that's a very good point. I totally agree. So for those who didn't get it, he's saying that the semantics have to be consistent, and here the domain is an actor and the range is a movie, and so we should have the same thing here. The domain should be a director and the range should be a movie. So really well spotted. Completely agree with that. Here's how I was building the N3 when I was building it, and it's a closed door. This is never going to go on the internet, right? So I can say what I want to say. That's it. I looked at the arrows. The arrow went from a movie to a director. I was like, the arrow starts in the domain and goes to the range, and I'm going to just from and to this thing. And why use the words domain and range? People are trying to be smart. We can use simple words, and Hemingway said simple words and everything. So that's how I wrote the code, and I agree this is an inconsistency. And thank you so much. Yeah. So. What we'll see is that this inconsistency has now gone all the way into the reasoner, and we're going to have to define bidirectional relationships or inverse properties in order for us to make sure that these kind of inconsistencies don't matter, right? We have right now maybe 5 classes, and there's so many ideas in this room, right? In a real-world scenario, a supply chain ontology is going to have like 60 classes in it, right? I'm dealing with a construction ontology right now, and there's a fantastic ontology called Bricks. It's open on the internet. Feel free to click through it. It's fantastic. But I'm dealing with a construction ontology with 200 classes in it. I don't even know what some of those things mean, right? I'm like, literally, I have no idea. So it's fun. These consistencies and inconsistencies will always be a problem for us, right? Because again, we're trying to get closer to how humans talk, humans think, but we're not there yet. The whole specific language thing hurts us. So, but thank you for spotting this. Is just, I can pretend I fixed that bug now. Yeah. Okay. So inverse properties. Now we have the word inverse of, right? And directs is an inverse of directed by. So we have a directed by property somewhere, right? Directed by. And then this is the inverse of directed by. So even if it was inconsistent, because it's a bidirectional relationship, you know, A equals B, so B equals A. Go ahead.
If there is already a relationship defined, like directed by, we still have to define domain and range for a inverse relationship because it's assumed that they will be flipped in the inverse relationship.
Right, and I might have done, did I do it wrong this time?
No, so
Director movie.
You don't have to define in two cases, right? Because there is already enough.
So you're right. We shouldn't have to. We shouldn't have to write code at 2 in the morning as well. This is where, like I said, there's a reason my knees are shaky, right? There's
like am I asking, like if you define...
You shouldn't have to, but it's always a good thing, right? So there's this idea of defensive programming. So let's just put all the constraints together so the reasoner can pick it up correctly, right? Plays character, character played by, right? So we're now able to go, you know, from the stairs, these are the stairs that go from the bottom to the top, and the same ones go from top to bottom again. So we're able to now define inverse relationships, right? And now I'm going to come to the reasoning part, the restrictions. And there's a bunch of these, but I want to make sure that we've crossed the bridge, you know, just the inverse properties. Yes, go ahead, sir.
So notice with the verbs that you have in here, depending which way you're going, you have like present tense and past tense. Should any consideration be given to verb tense?
Yeah, directed by. Yeah, so always prefer active voice present tense everywhere. I didn't do that here. But you're right. Thank you for catching that. So the question was, should we, because we're talking semantics, should we take care of tenses, right, and voice? So active voice, present tense, as far as possible, right? I don't know. How would you name this thing then?
As director.
Directing? Yeah, why not? Yeah, that's a good one.
Wouldn't it be as director? Or are you talking about?
Directs, has director, that makes, like we're still trying to model human language here, so. Any other options?
One way relationship is active voice, the relationship other around is like more like a passive voice. Or director directs movie, but movie is directed by. So that's what I'm.
Sorry, go ahead. I didn't capture yours.
So I think the director directs movie, so that's like a direct relationship. But if you flip it around, that's more like a passive voice. Like movie is directed by a director.
Yeah.
So maybe that's.
Yeah. I didn't, look, ontologies are best developed in a big room with a large team and lots of coffee. And otherwise, if you do it all alone at 2 in the morning, it's going to be this, right? That's not even a funny joke. It's a reality. So yeah, but thank you, sir, for that very, very, very important bit. So inverse properties, are we okay with? Should I move on to the reasoning part? Because that's going to need a little more attention from you. Go? Okay, we're going to rush through this one, right? But it's going to be super interesting, okay? So restrictions are of some different types. For those of us who played with databases, why is this not? I don't know why it's not zooming in. Oh, it does now. Can you see it? Okay. Right? So we have cardinality restrictions, one-to-one, one-to-many, many-to-many, many-to-one, right? Because it's a link, that's like the default, that's the first thing that comes to our mind, because we've all struggled with relational databases. The databases that have the word relationship in them, right? So cardinality, right? But what could some other relationships be? It could be cannot have X, can have X, and so on, right? So this, when you see OWL being written, you'll sometimes see those double caps, these things. So this is just a note that this is just indicating the data type for a literal, right? So just in case you missed it. So when we're saying things like this, cardinality will say 1, and this is a non-negative integer, right? We'll have exactly one value and one value, right? Make sense? Right? A movie will have one script. Even that is not true these days. But a movie will have at least one script only. That sort of thing, right? So movie ontology, right? Let's enforce some rules in the ontology. Every movie must have at least one director. At least one director. We can have the Avengers, which has 2 directors, right? We can have No Country for Old Men, which in reality has 2 directors but is named by only one director. So we can have all sorts of fun stuff, but at least one is required, right? So what we do is we have a min cardinality word defined in OWL, right? So the way this build came up was RDF was like the basic ontology, just like really bare bones, and RDFS added some extra words that allowed you to define a schema very much like a relational database does, right? And then OWL added reasoning words to it. So when we do reasoning, we always prefer OWL. I have some examples of reasoning with RDF, and it's really clunky, like you'll throw a shoe at me or something. Yeah, go ahead.
I'm just thinking about trying to form a question around, like, if I have data sparsity, like how this handles, what if I have lots of data sparsity, but in this example, like I have directors that I have some information about.
Right.
I have movies that I have some information about.
Sure.
But I may have a director. Let's see, every movie must have at least one director. What if I have, directors that I haven't yet tracked down the movies they're in, but I know I want them in my database, so I've added in like a director and their age and something,
right,
but I don't actually have it related to the movie. Like, can you put in sparsity, like sparse data, as long as it doesn't explicitly?
So yeah. So I'll repeat the question for everybody. So what the question is that what if I don't know the director's name right now, right? And I'm going to find it in some point in future, right? Just like an async await request. I don't know the director just yet, but I'm going to find it, right? So how do we handle sparse data, right? And the intuition is very simple. We're not talking data, we're talking schema right now. When we add data, it becomes a knowledge graph. So in a knowledge graph, in an ontology that's been hydrated with data, you can actually use multiple strategies based on the use case you're trying to solve. Right? If you're building a project plan, you don't know the task status because the task is in future. It's yet to start, so you have a default value there. Right? Or you can have like a null. Right? You decide how to handle nulls in your data. You decide how to have yields and async await type situations in your data, right? Because it will come to, it was never known, or it will never be known, or we will come to know about it, all those are knowledge graph decisions. In an ontology, we're saying, hey, there's a rule. And if I implement the min cardinality rule, you can't go ahead and hydrate an ontology without a director. So that's a rule we defined. We can, of course, remove that rule and, we can build an ontology like that. That's not a problem at all, right? But I think that was a very important question because oftentimes, and it's our habit as engineers, we get into the how and we don't stay inside the what, right? And like the next thing we'll open is a Jupyter notebook, so that's going to be like the epitome of how, because how do you reason about it, right? So we're going to see that next. Yes, I don't want to. It was internationalized. IRI is internationalized, not international, but it is a step down from universal. Come on, right? So internationalized, yeah. By the way, I didn't write it, right? Okay, so yeah. So do you see this log? This is going to be a fun one. So just like we had OWL, we had RDFS. Log, anybody want to take a guess what log means? Logic, it doesn't mean log like a server log. Today, log only and only means server logs, right, or mathematical logs. But back in the day, we're talking the days when database tables had to be 8 characters or less. I don't know how many of us have faced that. Sir, I'm looking at you. Maybe you and I are the 2 people in the room. But yeah, there used to be a time where you used to have like ATTR1, ATTR2, ATTR3, 3 tables with attributes, and only like the people who were running it knew that the first attribute is age, the other is address. And, the database couldn't have more than 8 characters, so, happy birthday to you. So yeah, log is actually logic. So the words it's adding is logic words, right? So implies, conclusion, includes, does not include, semantics. This is a log ontology. So a lot of these, so what we should be doing is when we're thinking about building our ontology, just look for openly available ones, right? I'll click on a couple of like a music ontology. It's fantastic to look at. It's so beautiful because you check out and you say, oh, somebody actually thought of that. Oh my God, it didn't click before, but somebody did that. So when we're thinking through these things, it's fantastic. Join us, sir. All right. So can you see that? Can you see how the rule gets implemented? We have the antecedent and we have the consequent. Fairly straightforward. Make sense? All right. Yeah, everything. Now, actor acted in movie implies movie has actor. Again, please don't look at my tenses. Look, I come from India. The English class was taught in Hindi. I'm not joking, right? So this happens, but don't hold me to it. If you ask me to do it in Hindi, I couldn't do it either. Like my language is shot. So anyway, but actor acted in movie, movie has actor. Right? So now we suddenly can reason about inverse relationships, right? We can connect. So we can calculate inverse relationships because somewhere this implies actually points to a Python function that says take the value of A and take the value of B and swap them and return the new tuple. It's that simple. Right? The implementation of the reasoner, you can imagine this log : implies is actually firing a Python method somewhere. That's just swapping A and B values in a tuple. And there we go, we have inverse reasoning. It's not that hard. The how part, I mean, and who am I to say A and B are simple things? A and B could be complex ontologies on their own. So swapping might be a very complex thing that will, earn you a medal someday. But the function names implies, right? If an actor acts in a movie, then the movie has that actor, right? Inverse relationships. We're in a closed world. We can't make the other assumption unless explicitly stated so. Why are we in a closed world? Because we want to be able to automatically reason about our data. And we'll see shortly how that enables us to integrate enterprise systems faster, search through things better, and LLMs can reason about these things. When we say large language models can reason, they can't. They can just do this part. They can just tokenize this stuff in a way that makes sense. So when you feed a language model an ontology, even a small part of an ontology, your responses will actually, there's like a RAG, R-A-G tutorial going on. I read the title somewhere. If they covered this stuff in that tutorial, right? So in the repo, I will have some examples. I'm not going to cover them in this tutorial specifically, but if you follow the repo, it's going to have a lot of these examples where we'll show how AI, and especially these agentic times where there's a movie agent and there's a director agent and there's an actor agent, every class can be its own agent, will need ontologies to understand what the restrictions are, what the rules are, how the processes flow. Right? Very important when we get into the business part of things, because when we're doing process mining, when we're doing optimization, when we're doing any kind of business transformation, this sort of stuff is like bread and butter. This sort of the key stuff, right? So what did we build? We always build these 7 things and no more, right? So at a high level, that's all an ontology is, like these 7 things, right? Hard? What was the hardest part till now?
Syntax.
Yeah, syntax is new to us, so I agree. It's hard. To me, the hardest part was defining ontologies. Right? I don't know, come on. If I go through a syntax again, you'll start recognizing it now. In fact, you'll recognize it in the next one right away. So without wasting too much time, I don't know, how does it work? Like we take breaks or okay, yeah, go ahead.
I don't know if this is a quick question or not, but when you do the prefix RDF or RDFs, which is essentially an import, and then you use RDF's :label.
Right.
If you go to the actual RDF file, is that just another N3 that uses the same syntax we learned here, or is that?
Yeah. So let's open up RDF. That's a brilliant question. So the question is, when I use any of the words defined for me, RDFS subclass off, right? That's a word that this ontology defines. And we're saying we're going to borrow the same, we're going to continue to use the same meaning that this ontology defined for this particular word, right? We're importing all the meanings from a different ontology. So if I go to RDFS, oh, come on. Google RDFS, close your eyes, you shouldn't be seeing my windows, right? I'm sorry, do you remember what the word was?
Subclass of. Actually, subclass of was RDFS.
Oh, it was? Let's just Google that thing then. So we're using subclass of this thing. And that's the meaning of this word, right? So is an instance of property, which means subclass of is a property, which means it can be both a data property and an object property, right? It's a property, right? And it is used to state all the instances of one class or the instances of another. Right, so it has a specific meaning that everybody agreed to, and we're just borrowing that meaning in here. But that's a fantastic question. So we actually get to see the mechanics of how we're building meaning into our thing. I should be more fluent with this thing. So sorry for all the fumbling. You guys are an intense set of engineers, so yeah. Yeah, go ahead, sir.
If you have a property and an inverse property defined, like let's say for like directing or acting, does that serve the same function as a reasoning rule?
As
a reasoning rule.
It will enable us to reason about it. These are just properties, right? So the question is that if we have a property and an inverse property, right, is that not enough? Is that not reason enough? Because now I can say function and inverse function, right? So the example is directed by and directing, right? So is that not reason enough? So these are just properties. Reasoning, when we say, would effectively be the name of a function or a method or a logic that we'll call someday to verify and validate. So we're going to say, is this inverse property consistent in the data that I have received? Jurassic Park was directed by Steven Spielberg. Joel Cohen directed Jurassic Park. Data is not consistent, right? So because I can get property and inverse from two different sources, remember, right? This happens quite often in things like insurance or things like supply chain, because I get my invoice and I get my supplier slip, like completely different. Or in banking, right? There's a customer onboarding system and then there's a credit card system that don't talk to each other, right? So properties and inverse are just data. We need to then build a reason around it. Any other questions before we get into, like, yes, sir, go ahead.
I've heard a lot about syntax, and I know that JSON is a really common...
I love where your mind is going, yeah. Thank you.
So
absolutely, yeah.
JSON LD, I haven't heard anything mentioned about that. I guess, what are your opinions on that?
Yeah, here's my opinions about that.
And then,
that...
kind of the second part to that?
That's a JSON LD. It's there.
Yeah, JSON. Okay. And what do you think of using JSON schema to define?
I actually, so practically, so the question is, what do we think of using JSON or JSON LD as a way to describing ontologies? I like it, right? But I also know that I was not at the top of my class, so I know that there's at least 70% humans on the planet that are more intelligent than I am, so I might be missing something. But I like it. I think it's a very natural way of writing ontologies, because these are nested things that sort of live within each other. Another way that I would like to describe ontologies is through raw Python code. Just Python as a language lends itself very well. So imagine a .py file being your ontology. You can just import RDF, import RDFS, import OWL, and then say, here's my classes, here's my data classes. Like, Python actually has the semantics to represent an ontology. I have not been able to crack that. Like, I've not been able to break, if I create an ontology referred as Python code or JSON code, something breaks. In my experience, it did not. But, that's the size of my brain. And typically, that's the size of a regular brain, right? So I might be wrong, right? Did that answer your question? Yeah, thank you. Any other questions before we move on? Yes, sir.
So I feel like this is probably a very basic question. What is it that having a very well fleshed out ontology really offers you? I understand that you talked a bit about this idea of like, oh, you can query it in a way that like querying relational tables might be pretty messy, but is there something else that one gets out of having these?
Yes, yes. So the question is that, where does this lead us? We have a really well fleshed out ontology, but what's the value? I'm not seeing the value. Like I said, music ontologies, when you'll go like, I'm about to fall asleep, and it'll be like, that's what we were doing. We're going to start that now, right? So how much coffee do we need here? Or can I just start, and like when the first person falls asleep, we'll take a break.
How about a 2-minute break?
2-minute break? All right, let's go do that, yeah. But thank you for the question. That's a really good segue into the next part, so yeah. For those of us who are still staying around, do you mind taking a look at the music ontology in the second folder?
Could I ask a quick question?
Sure, go ahead.
Just because you keep saying reasoner, I'm wondering, does this have any relationship to, I mean, I know it does to some extent, but when I kind of look into the history of like good old-fashioned AI, symbolic AI, where there's...
It's exactly that. Thank you. Yeah. Yeah.
It's all these building these core relationships and their nouns in such a way that the inference engine...
It's basically symbolic reasoning.
I see.
And so we're doing that now. What we'll do is we are going to use already. I like that name, right? Already to absorb our ontology, add data to it, and then reason with it. So we're going to actually see what reasoning really is, you know. And then what I've done is I think for the first 5 or 7 ontologies, I've actually created reasoners. This is a proper reasoner that has all the rules and everything. So if you're really bored and you want to read some Python code, this is ready for you to review. So this is actually there. And I have somewhere I define all the rules. So this data class is data class, data class. So this is where we're computing the inverse relationships, fairly straightforward. And there is, give me a second here. And then there's a set of these rule XX. You know, I should be really using VS Code, not this, but okay. So this is where we're computing the inverse relationships. This is just literally, because we have defined, it's enumerating them, and it's just literally this Python code gets called, right? Song, artist, artist, song, inverse relationship. And then we have all these rules. No, yeah, there we go. So now it's just each one of these rules will get called based on what was there in the ontology, and that's the reasoner, right? So every time you add a piece of data, all the rules get run.
Right.
And we're going to say, okay, this was consistent, we move on. Oh no, this was not consistent, we hit. So simple as that, right? What Tim Berners-Lee could do was he built a general purpose closed world machine reasoner that you could use with any ontology. What we're doing here is I'm whetting your appetite by building 3, 4, 5 reasoners with you. So we know how this thing works, and then we can make a general purpose one, like, right? But we're not, like, I'll not get here. Let's just first start with the already one, right? For those of us who are kind of bored, kind of just sitting here, Do you mind looking at music? O2 structure, dot markdown. So just as like I don't think it's a hidden thing, but like games have bonus levels. The movie's ontology, I built a second version of that ontology using the movie lens data. Do you know movie lens? Right, movie lens data was where they collected a lot of ratings from different users and asked them to also tag the movies. So, Home Alone is a Christmas movie. So Christmas movie is a tag, right? So users added those tags, and then they enriched that with random machine data. So movie lens has been used in a lot of recommendation engine contexts. So what I did was in movies, I've also built a movie lens ontology, and I made a lot of mistakes here, so I made here. So just, when you're trying to click here, somehow your mouse will slip and you'll go, oh, I clicked version 2, all right? Never click on version 1. And simple ontology, right? And here, you'll see that we have fantastic rules. We're taking it to the level where we can actually build recommendation engines. I'm not even joking. We can build recommendation engines just by defining an ontology correctly. It is really cool, but we already are running low on caffeine, right? So I'm here all day today, and please keep in touch so we can build something really cool after this one, right? I would really hate for this to be a tutorial where we just, yeah, we had a tutorial. Let's continue to develop together and build really cool stuff here. So there's a recommendation rule somewhere. So it can, for example, there's a objective definition of whether a reviewer is too critical or not. Check that out. Or there's a similarity calculation, right? So we're saying, hey, this person and this person both like horror movies and fantasy movies, so they might also like. So collaborative filtering. So I remember putting in a collaborative filtering rule. Collaborating filtering. There we go. This thing is actually this used to be one of those questions that Facebook, there was no Meta back then, Facebook would ask in their annual hackathon to hire programmers. That's the code. Come on. You're basically using ontologies to build a recommendation engine. How cool is that? Right? So again, probably not for this workshop. Somebody's going to get really annoyed really fast with this stuff. But that's, explore this when you get a time, right? For now, what we're going to do is we're going to move on to ontology number 2. Should we, or should I wait for another 2-3 minutes?
Can I ask a question about all
Go ahead.
those rules before you move on?
Go ahead,
So,
yeah.
I think maybe I'm just missing at what point those, what do those get? I mean, I think, again, as with my last question, I'm getting stuck between the ontology and sort of the application of it. But it seems like those rules would all then, I don't know, it's a way of generating data that you would never input, right? It's generating additional.
Correct. So the first, and thank you for asking, so the question is that all these rules would end up generating the data that was never there in the first place. So typically, the way humanity has solved that problem is through lots of programmers just, talking to each other and, getting divorced and turning alcoholics and managing views in databases and so on and so forth. But we've had to compute these properties. Now we have a way to just specify the rule, and the reasoner will automatically compute these properties, check the consistency, and maintain this additional data for you. And we'll do that. We'll do that in a minute. So this part is where we are going to open up a music ontology, and I'm going to walk you through the first OWL-ready application, right? Where we're going to create our music ontology. We're going to see the parts of it from an engineering, like from a Python code perspective. And then we're actually going to compute or derive these properties, right? And we'll see the moment you add more data, the properties get automatically created. That's pretty cool, right? No more views, no more Java classes, no more alerts, no more triggers. Oh my God, life is so much simpler. You could just write some text and then write good Python code and you're done. So yeah, so this is pretty cool. So music, I'll maybe take, do you have a question? Sorry. No? All right, sorry. So music, very, very quickly, I just want to, again, we'll go with the structure, right? I just want to show you, without having to learn N3, I just want to write what's in my head here. And the gentleman here is absolutely correct. I should have used JSON better, or Python even better. Right? But this is what it looks like. So there's all these songs. There's a single's a song that's like on its own. Then there's an album. I can. And a song has artists. A song has a genre. One song can have multiple artists. There's an asterisk here that nobody can see. One song can have multiple genres. An album can have multiple artists. An album, oh, this is incorrect. One song cannot have multiple albums. One album can have multiple songs, sorry. So there's a bug there. But that's the music ontology we have, right? So very simply, it looks like this. Right, and in a second we'll look at it in N3 where we have additional rules computed for it, right? So fairly straightforward, like we have artist, album, record, label, genre, award. Not hard, right? Okay, here we go. So within the music folder, I want you to look at a very quick intro to OWL-ready. This is not quick, but I'm just trying to keep you excited. Right? So I'll switch to Jupyter Notebook now. So for those of us who don't have OWL-ready, you can just uncomment this line and Control Enter. OWL-ready will bring Java jar files along with it, because one of the first reasoners that became really popular was called Hermit, and that's a Java reasoner, so it needs JDK. What I've done in this file is, if you don't have JDK on your laptops, we have an alternative. So you should be able to go through this entire thing without installing JDK. But if you do, I'm just saying that OWL-ready comes with a bundled reasoner, right? Again, I'm separating the what from the how. We have to see how reasoning works and not Hermit the reasoner, right? So we can all Google Hermit API and learn how Hermit the reasoner specifically works. It's just like learning N3 versus learning to write an ontology. So I'm just trying to optimize for what right now, right? Once I know how to reason about an ontology, I can use any reasoner. I don't even like Hermit so much. I prefer EYE, right? So, okay. And then we have basically date time and OWL-ready. Okay. Sometime in this workshop, you will see Hermit complain about date time. When Hermit was built, it could not handle date. It could only handle date time data type. Right? So that's just old clashing with the new. We'll ignore that part. We'll like close our eyes and just scroll down. Right? In my 22 years of my career, countless bugs have been fixed by just closing your eyes and scrolling down, and then checking your code and move on to a new job. The bug gets fixed, I don't know, magically. All right, should we start? So here, we're not building the N3 again. We're going to do everything from scratch, but in Python, right? So let me know when your notebooks are ready. Okay. So we create a new ontology by using the word get ontology. This is an already just API, right? So instead of saying new ontology, they just say get ontology, right? And do you remember what this was? IRI. The I was internationalized. So this could be a series of emojis and it would not matter, it just works, right? And now we're defining the classes. How do you define a class in Python? The way you define a class in Python, right? So suddenly creating an ontology is super easy, it's super clean, right? We're just doing class, pass, because there's like literally nothing inside the class. Why can anybody, just intuition-wise, tell me why are we not defining properties inside a class, like we do in object-oriented programming? Why are we defining properties outside a class? It's such a thing, it's such an aha thing about ontologies, but I'd really love your opinions on it. You know the answer. I promise you know the answer. Just let this and this connect.
Are you asking about the song class or?
I'm saying why are the properties defined outside the class? Performed by is a property. A song performed. Go ahead.
Because it defines relationships between separate classes, right? So.
Just there. You know the answer. I'm telling you, you know the answer.
That property can be used. It can be referenced to multiple places, right?
Sorry, do you mind saying that louder?
A particular property definition would need to be referenced to multiple places.
Thank you, yes. All our words have to be unique. We're defining an ontology, we're not defining a class hierarchy. We are defining a vocabulary, right? So in a vocabulary, there's no structure, there's just all the words are there, right? And all the words have to be unique because a word, like you very correctly said, can be referenced anywhere by anybody, right? We are here not creating like a tree. We're just creating a flat series of vocabulary, right? So the two words we had to remember always were declarative and vocabulary. Right? Okay, move on. Are we past the 1 hour mark yet? Are we? Oh, that's probably the most amount of study I've ever done in my life, yes. I'm feeling very proud of myself. All right, you guys are like proper committed, like, okay. So thank you for giving me your time is all I'm saying. Like I'm feeling a little grateful right now. Okay, so do you see any problem with this code right away? Say yes.
Yeah, everything has to be defined everything is defined between with the list like array, even if it is singular. And I see the str is the word that is.
That's the engineer talking. Okay, that's a what? That's a how. Anybody see a problem here? Go ahead.
Is it
Thank you, yes. Let's see if that breaks things downstream, right? Okay, so we run this. And now we're going to create an instance. So this is where we start hydrating our ontology, right? We created a really simple ontology, and now we're going to start hydrating it, okay? So Bohemian Rhapsody is a song, and we're going to give Queen as an artist, right? I'm really sorry, this is the song somebody was playing on their mobile phone in the flight I had from India to Frankfurt, because that's the song their infant sleeps on. I used to like this song, I hate it right now, but that's the song that came to my mind when I was writing this, so please excuse me. If you have a better song, use that, all right? We basically have a song and an artist with a song, right? Right? So what are the data properties of a song? It's got a title and it's got a performed by. These are two data properties that tell me what a song is. The focus is not how, the focus is what. We are still defining the ontology. We've now defined it three different ways. We've defined it just in a loose YAML-ish format to make my comprehension work. Then we've defined it using N3, notation 3, which Tim Berners-Lee really liked, because it could also specify rules and semantic relationships, this, that, and the other. And now we're defining it just pure play Python. Make sense? So I can now print Bohemian Rhapsody as a song. That's just like a really simple thing, right? Oh, do you guys want to do this? Do you guys want to see the ontology API that Already class provides? It's interesting, but it's a lot of scrolling, so let me do that. So you get a lot of interesting stuff, and a lot of it would be reasoning based, right? So you'll see things like disjoint classes, right? You'll see things like inconsistent classes, right? So we're basically, within that ontology, we're keeping a map of the classes that don't match with each other or are inconsistent as far as the rules are concerned. So when we don't know the director yet, that time for that piece of data, we go into the inconsistent class. So it's represented, but we know that a rule's broken over there. So makes sense? Can you relate A to B now? All right. So a lot of these interesting things come up. The most interesting to me is the word world, because in every trailer there's in a world, right? So the default world inside Already is called default world, because we don't know how to name names, right? It's called default world. They could have named it universe. They could have named it something fun, fantastic, but they called it default world because, come on, why be creative, right? So okay, so getting back on track, or trying to, let's now look at namespaces. Go ahead.
Sorry, the output says performed by music.queen.
Where did that?
The output of where you have it printing the song is Bohemian Rhapsody performed by.
That.
No. Down. Like right before you showed us the ontology, where you have it print. Yeah.
Oh. Yeah, that's the ontology dot, Queen is a part of the ontology. Make sense?
But why is that Music.bohemian Rhapsody.
Yeah, I'll have to check. Performed by Queen. Queen's an artist. Artist is a thing, and thing belongs to music. So if I had one more class here, it would actually say, because it's, I think, the range. Range is the artist, right? So performed by range. How do you refer to the range? You go to the ontology and then, walk down the connections. Make sense? So if I had, give me one more class. Right, and let's add one more property here. Belongs to. Make sense? I don't know, how would you say a song features on this album, right? And we'll say domain equals song and range equals album. Right? And now, when we build the ontology again, we're going to say, do you remember the name of the album where Bohemian Rhapsody featured? Nobody likes that song. I don't understand why it's such a hit. Infants sleep to that song. A Night at the Opera. Thank you. A Night at and I'm going to say small a. Dot was a feature zone. This thing. So how is this variable going to get referenced? It's going to say, hey, I'm an album. What is an album? I got to go to the music ontology, and then it's going to say, okay, music has a class called album, so music.album, right? So let's now try and print that. I'm going to say like that, and say Bohemian Rhapsody features on, right? Shift enter, music dot. Make sense?
Just because the song is a string, is bringing the string. Is that right?
No. No. Here's a simple question for you, right? This is going back to object-oriented programming. This, whatever, forget the keyword class here for 30 seconds. What is this? This is a property of this ontology. There's something in the world called ontology dot, right? Just like we define an object, right? So the big object that we've defined is ontology, right? And it has, see this context manager, right? So it has all these ontology, music.song, music.artist, music.album. So whatever's in the range, how do you resolve a range? You go back to the ontology and then you walk down. That's how OWLReady does it. But that's well spotted. But did you understand the mechanics? Let's move forward. I promise you'll start liking it, all right? So here we go. And namespaces, right? So what was the ontology about? Just defining music stuff, right? We want to be able to say, everything within this namespace is consistent and in terms of meaning, right? This word has one meaning and one meaning only. This relationship has one direction. This particular function has one implementation and so on, right? So basically namespaces is where we define that part. The fun begins when we start merging two ontologies. So do you remember when defining N3, we imported 3 ontologies? Do you remember? So when we were doing N3, remember how we prefix? We imported multiple ontologies to say, hey, this one defines all the relational words, this one defines all the math words, the log was logic, and so on, right? So how do I do that in Python? Right? I'm creating an ontology from scratch, so I want to be able to merge 2 ontologies, okay? I just load that ontology. It has a standard IRI, right? So if you have an internet connection, FOF gets loaded. FOF was a friend of a friend ontology that, like I told you earlier, is still used to the day, right? In fact, the original website for FOF is probably down. It doesn't work. But the ontology itself works, right? There's also a fantastic data set that you'd like to play with. This is actually all the linkages that they had created using FOF. So you can actually just use FOF, hydrate it with this data set, and actually play with it. That's a lot of fun, right? But let's load FOF here and see what it has, right? Just for us, here's all the classes defined inside this class. The word class here means an ontology class, not the object-oriented class that Python has. So let's keep that difference in our heads straight. This class is actually a property in Python. Make sense? The word class is used in the context of an ontology right now. You're going to need more coffee in like 30 seconds. All right? Okay, so we import FOF, and with this we just list down all the classes that all the words, the vocabulary that FOF has defined. We're going to see what that is in a second. Here we go. So FOF has standard definitions for the following words. It has the word class. I don't know why it has person twice and agent twice. I'll have to check that. I'm not, what do you call a person who's like really diligent on like the minutiae? Conscientious. Yeah, I'm not that. So yeah, so I'll have to check. All right, but it has spatial thing. It has document, organization, project. Why it has this again and again, I don't know. Personal profile document. It was used to link websites together. Friend of a friend of a friend of a friend. That's how they built the Wikipedia graph. Wikipedia can still do this. In fact, if you look at Wikipedia code, sometimes you'll see FOF come up, right? And here's the properties that it gives. How many of us recognize these things? Come on. Right? Takes me back to when I had black hair back in the day, right? Or I had like 0 bald spots. Yeah. So all of this is there. There's probably a pager somewhere. I don't remember. I don't remember anymore. So yeah, but do you see how it's already thrown a warning? We know that's a problem with VOF. But it's so old and nobody's touched it in so many ages, and it's such a standard that we're gonna have to just live with it. The guy who knew why retired and moved out of the country. And we don't know who he was, right? So yeah. So this is an example of, like, just tech debt that has been handed down from generations. But if we in this room can come up with a solution, guess how many zeros will follow one in the paycheck that we get? Incredible value to be mined, because we've just completely sidelined the ontology space in trying to do everything else. Here was a very, very straightforward idea of building a knowledge graph, right? So yeah, just solving that. So this is what I'm trying to say here. Also my rant that you can't write poetry this way, but one word has to mean one thing in one world. It's just the stuff that we're living with. Today we can do smarter things. There has to be an ontology squared or something better, right? Where we can see context before we decide the meaning of the word, right? Remains to be seen. So now what we do was we just use imported ontologies.append. Effectively, this is like a list where you've just added one more thing. I'm going to test that, right? We can, if we create, did I run that? Yeah, I did, right? So I'm going to just add it. And if I, like, .append tells me this is some sort of a Python collection, right? So if I do a type, oh, come on. Can I do? So it's probably a list with some facade on it, right? I am, stop going to, and now, see, ontology, which means for us, context managers become really important. So you'll see me use this again and again, with. It will become painful, but I'm just trying to be diligent. When you're writing Python code, you write one with at the top and just everything follows. Here, because we're using a Jupyter environment, we'll have to repeat that again and again, right? So with ontology, we can now say musician is a child of a person. Person is a faux vocabulary. Make sense? So we just did that same thing that we were doing in N3 using pure Python, right? And we're familiar with Python. Somebody said syntax was a problem earlier. This is Python. This is really cool, really easy, right? And now, Freddie is a musician, Freddie Mercury. Freddie has a name, which is Freddie Mercury. This is a faux property, right? Friend of a friend property. Right? And this is what I was talking about. In a world, in one world, one word, one meaning, right now, all the ontologies are gathered into what is called default world, right? You can define your custom worlds. This will especially be true when you're looking at mergers and acquisitions type business cases, right? Where the world of company A is different from the world of company B, right? So in a lot of these audit and compliance type situations, you're going to run into these multiple world situations, right? For now, everything rolls up into one world called the default world, right? So we can say, when we do get ontology, we're loading both the ontologies into one world, which now means if there's a vocabulary clash, we have to solve it. So we're loading ontologies with the explicit knowledge that there's no vocabulary clash. If there's clash, we're going to prefer the open vocabulary first and then define our vocabulary slightly differently. Make sense? So FOF has a name, so we can't use name again. We'll use FOF.name, right? And if we have to name names, then we'll have to create some other word for it. Make sense? Too confusing? We'll see an example in a minute, right? Hey, we're writing Python code. Look at that. It just took 2 hours. So we see all the ontologies loaded in my default world. And we see all the individuals we've created. Individuals is another way of saying instances of a class, right? And we're saying all the classes across all the ontologies is 36, right? So when we say, hey, what are those 5 ontologies that got loaded? I thought I just loaded FOF, right? I run that, I know that there's an anonymous ontology that gets loaded by default. There's an example, music owl, that I defined. FOF is there, RDF, and example. I don't know why it's twice. Yes, go ahead, sir.
I'm a little bit confused as to how these things get loaded. Like if I follow the ring, or the IRI, I guess, I'm not sure what it's taking me to and how that relates to what it's bringing.
Yeah, so there would be some name resolution here. I don't think this is an actual website. This is just name resolution, just as people who've worked in XSD. This is probably a DNS thing. This is not taking you to, there's not an actual site at the end of this. Right? We just had like an example.org/music.owl. It is just trying to create a unique variable. That variable will resolve to somewhere in the internet. In the case of FOF, it's probably already embedded already.
So these things are embedded inside the OWL?
In some cases, not all, but in some cases. So there's a fantastic music ontology that we can use. Give me a second. I'm trying to give you an example of what would not be available by default inside already. Oh, there we go. So this is a proper music ontology that, big people met and agreed upon, right? This has lots of properties and classes in it. This is like kind of fantastic. You can actually look at the classes and the properties and the individuals in this thing, right? So because there's this site they decided to use, Perl.org, right? This actually has a web page behind it. But other than that, it's not there. So for example, I can load the same site same ontology from GitHub. There's got to be there we go, N3, right? I can just copy paste this into a local file and I would have loaded the same ontology. It doesn't have to go to the web. But the IRI remains the same. Make sense? Make sense? Our IRI is kind of like a name resolution that's happening. What's actually the handle for a website? It's the IP address. It's not the name. Google.com is a friendly name. It's a resource indicator. It's not the actual handle of the website, right? Similarly, so the whole problem was I have to keep creating unique identifiers, unique friendly names, and the friendliest that we thought, which is really ugly, is use the URL format, but just use Unicode everywhere. Sorry, go ahead.
Oh, so is the IRI defined somewhere in this file?
Yeah, yeah. They would have music somewhere.
But is there usage of HTTP actually invoking hypertext transfer protocol? Like, is it?
No.
So that's just.
It's just a name.
Just a convention.
Yeah.
Kind of stuff.
Yeah. I know. So yeah, so it can, if it has a web presence behind it, but it doesn't need to have a web presence. We're just trying to talk semantics here, right? So sorry, go ahead.
Somebody like you writing like this entry, how does he know what are the available, like what is the easiest way to know?
Yeah, thank you. That's a good question. So the question is, how do I know what are the default ontologies already available? And what you do is you say, open web ontologies. And you get here. And it gives you a list of ontologies. It's like a good ontology or something like that. Vocabularies. There was a good ontologies site. I'll find the link and I'll add it to the repo, right? But there is a site called Good Ontologies. There we go. I don't think this works anymore, but look, the open ontologies is so old. We did not have iPhone back then when they stopped working. So a lot of this stuff is broken, but is still being used, right? So we have to kind of, the whole goal I had here was to start a conversation with some brilliant minds again. It can't be that I'm using 21-year-old code to reason about 2025 data. Bad idea. We got to write something better, right? And, you know, we're it. That's it. We're the ones who know about it. So we better try something, right? Yeah, good ontologies. Thank God I found it. Yeah, so I used to use Dublin Core quite a lot. I used to work in education back in the day. And Dublin Core was built to relate educational resources, right? If your child is bad at studies, it's probably partially my fault. Don't hold me to it. You know, I was in a different country. My English is bad. Some excuse, right? So, but Dublin Core was used to connect educational resources, and I did quite a lot. FOF, again, many of these links will actually not work, but it's pretty good. The music ontology also features here. And it would be fun to explore the site, not right now, but like whenever you get time, right? Hopefully that answered a little bit of your question, right? So go ahead, sir.
I don't see schema.org. Is that?
Schema.org should be either here or somewhere, but schema.org is another project that hosts ontologies. Right? So we can just keep using schema.org. And schema was the first proper attempt at building ontologies that were business focused. Not general purpose, but business focused. Friend of a friend is a general purpose knowledge graph ontology. Right? This one actually went into things like medical, and I think I may be misremembering it, but in COVID, I remember there was a protein or something they found through these ontologies saying, hey, these two things are connected, probably this could be effective in COVID. And so we could search this before mankind actually derived it and said, yes, this compound's effective. So had we continued to work on ontologies in COVID, who knows, the research would have been a lot more effective. But we'll have to Google that, but I think there's a case study where, and I was like, what? So there was some protein, they said, hey, maybe this thing, protein or some drug, they said, hey, maybe this is effective. And later on, turned out, yes, it was. Probably ivermectin, I don't know. Something like that. So, yeah, go ahead.
If we wanted to, like, make an ontology and then make it available through this get ontology function from OWL, how would we, like...
We're doing that right now. So that's the, yeah. All right, let me get back to this thing. So let's load the music data. What I've done is, in preparing for the tutorial, and that code is also in the repo, so you can go ahead and study that. There's no behind the scenes happening here. But what I had done was, in the music file, in the data folder, I guess, there was an RDF that I had created. Oh, no, RDF output. So here I have created like really raw, really bad music data. Actually hydrated ontologies, right? So there's an RDF that's actually, if I load it, is like this, you know? So it's with artist, whatever, collaborates with this. So it's basically an entire ontology that I hydrated, right? Right? The code for building this is also in the repo, but for now, what I want to do is just load it into my music onto, right? Very, very simple. So this is what, like you asked, if I have created an ontology and I want to load it, I just do .load. And there we go. And these are all the classes that were found in that RDF, the hydrated RDF with all the data in it, right? So if somebody wants to say that we didn't load an ontology, we loaded a knowledge graph, you're right. We loaded a knowledge graph because it has instances along with schema, right? If it was just pure play schema, we would have loaded an ontology. If it's got instances with it, right? Even if it's just a couple of examples, it's a knowledge graph, right? So we just loaded a lot of instances of an ontology, so it's kind of a KG, right? So same thing, we can look for the properties, and we have so many of these properties now, right? Again, can you see how sometimes the domain range is not defined at all? Right? Real world data. We don't have a directory yet. Right? So it's actually true. So what will happen is sometimes they will fail reasoning, and we'll see that in a second. Make sense? Yes, go ahead, sir.
I see that's an XML file, the music ontology.rdf. When did we create that?
We didn't create it as a part of this workshop. I had created this yesterday night, so we could just use it today. The code for that is called RDF Manager. If you want to explore that later on, it is, come on, somewhere here.
And then RDF ontology manager of PY.
Yes, thank you. Can you see that? I can't see that.
3 files up from what you selected.
Oh, yeah, there we go. Thank you. Open. That's the code. It literally, you know, just how you save Pandas CSV files, you know, dump, it just does a dump afterwards. It structures the data and then just does a dump towards the end. Right, so it's not hard, it's available, and it's just tedious. It'll just, create the ontology again, check consistency. If consistent, then write the data, all that stuff. So it's not that complicated. The higher order bit is coming up. We're going to write queries on our data. That's so cool. Now we're using the ontologies. Check that out, right? The queries will be, I think, mostly Python, but I've tried to add one Sparkle query. I don't want to get into the syntax of Sparkle. I will have, within a week, a couple of notebooks, very detailed notebooks, on basic and advanced reasoning using Sparkle. So we'll get there. Right now, the focus is building ontologies, using them with our bare hands. This is right now bare metal. We're focused on the what, right? That's why I'm using a really simple code, okay? There is a helper method that I've created, which is just going to format the Sparkle results for us, right? It's really trivial, right? So I'm going to hide it again and find all songs and their performers. If I were to kind of hide the cell, I'm telling you, you already know how to write this. I'm not even joking. Do you want to try? Just for kicks? I know you can see the answers. You have the entire repo with you, but just for kicks. What are you going to do? You're going to say, hey, if my artist has a signed to, and that signed to has a property, is not empty, right? Just to my list of results, append that artist's name. Right? Come on, we don't even need pandas for this. This is really straightforward. This is the code that you would write in high school. Right? Somebody has to say it makes sense. 2 people are smiling. Yes, victory. All right, 3 people are smiling. All right.
Can I ask, sorry, I'm
Yes,
just going to keep asking questions about
You should. Yeah, thank you.
That's the universe that I live in. So for this sort of query, it is always a first step to say, if this field exists and it's, and it's empty, you always have to check, the ontology doesn't,
Sorry.
create the, fill with default values, or, right, because it...
Yeah, so, okay, so I think what you're trying to ask, and you can correct me if I'm wrong, is we don't know when or how the data is getting created. Mm-hmm. So what are the checks and balances? What are my guardrails? When I query, what is the guarantee that this is consistent? That's why we have non-negotiable rules. And we'll check those rules. We'll define those rules, and we'll check them. Right now, this is just free form. We loaded some data. We are querying that data, right? But now we're going to define those rules and reason through them and say, hey, is that consistent? Yes or no, right? That's towards the end of this page. So, just close your eyes and scroll down. Sorry, go ahead, sir.
So I guess kind of on a similar note, when loading your data to build the knowledge graph, is there the option for any data items, their attributes or properties, if something wasn't defined in the knowledge graph, that it could get populated with a none or undefined? Therefore, that property would exist, but it would have a value that we can check.
Thank you. So I think the question is that what if I could default to a string which satisfies the rule, but it's meaningless, right? So if I put in NONE string when hydrating my ontology, I can always make that mistake. You're right, right? That's where we'll have to define additional rules. That if it is also not NONE, if has attribute performed by and song performed by and song performed by is not equal to none, none, then do the rest. Right? So it's just like data cleanup in a regular scenario. Right? But we can reach to properties that were not available in the data in the first place. We can reach out to inverse properties, derived properties, and make sure that we can check against those as well. If we don't catch it in the forward property, we can catch it downstream in the inverse one. We'll see all of that happen right now, but that's a great question, I think, and so did you. The process of hydrating an ontology, I suppose we'll have to look at that code, but I can walk you guys through after the, like if we're still up and running after 4 hours, let me just walk everybody through that code. All right. And I'd love to walk you through a reasoner because that's pretty awesome as well, but let's see. So query 2, this is really interesting. I want to like kind of dive a little deeper into this one. So we're saying if an artist has an attribute called signed to, right? And that signed to is not empty. Append the artist's name. So when you run this query, what happens? There's labels in the data. When I look at the CSV files, you know, there's labels. There we go. And when I look at artists, artists have a label ID. Right? Some of them have labels, others don't have labels, so we have a good mix. But we have an artist and label connection in the raw data, right? But here it's kind of breaking. I promise you this was not a bug. I deliberately wrote this just to highlight a few points. And this is the only complexity that we will come across as ontology engineers. This goes away the more we start relying on open source tools, because those tools have standardized these processes. But the problem is that most of these open source tools are outdated by at least half a decade, if not more. Right? So it's upon us to bring them back to life. Right? So how do you debug something like this? Any ideas? Again, you know how to debug this, I promise you. You'll see it in the next one and you'll be like, oh, that. So, but let me walk you through because this goes back to the reasoner, right? So, I'm not skipping it in the first iteration. I don't know why I wrote that. No, this is an advanced workshop. We're not skipping this. Okay, what could be reasons? We just logic through this, right? No artist instance exists, or no labels exist. In the RDF that I created, maybe they didn't get translated. So when I run, it says 100 artists found and record labels were 0. What? But we just saw labels were there, right? So what gives? So how come we don't have any record labels associated with an artist, right? So when I look in my reasoner, there's got to be a reasoner somewhere. Yeah, there we go. So this is at the heart of creating data or reading data and everything, right? This reasoner is going to figure out how to read all the CSV files and create the RDF, how to read the RDF and check for consistency and so on. So if I look at the outline, And there's got to be a validation somewhere. Let me do that. That inverse relationship I didn't implement. So do you see how I've actually commented out the code? Closed world model, I didn't have an inverse relationship, so it could not map record labels to artists correctly, consistently. So even though inverse relationships are computed, because I blocked that code, it didn't go into the RDF, and hence my queries, like you asked, are giving me error results, right? This does not happen with general purpose reasoners, because they're built to not do X if there's inconsistency, right? Like I said, let's modernize those reasoners. Go ahead, sir.
I think you mentioned earlier, the existence of graph databases, which have this same sort of structure where you have entities and their relationships, and when you're using a graph database, it is able to compile your schema and tell you if it's valid or
Yeah.
So, are those not?
They are.
Basically reasoners, and if so, what?
So actually you're right. And the question is that, hey, aren't graph databases the same thing? And you're right? There are two problems here. Number one, we don't have a distributed graph database. I don't know if you know that. Like, do we have a distributed graph database where we can have node A on one machine computing while node B is on another machine computing, where we can parallelize these queries? I don't think so. So we don't, number one, that's the problem. Number two, graph databases can work without a schema as well. So you can actually have a knowledge graph without an ontology, which means reasoning goes out the window, right? So because graph databases, Neo4j, there's, I think, Kuzu or Yuzu, I don't know. So there's a ton of them because they were created to solve a different problem. They were trying to do JSON-like operations with data. They engineered it differently, right? But you're right. Graph databases, if you open the code of any open source graph database, you'll start seeing a semblance of a reasoner built inside. It depends upon the data types, it depends upon the definitions, and it depends upon the inverse properties. But what it does not do is infer properties on its own. It doesn't do that. It will not derive the properties for you. It will just check if the data exists or not. At least to my knowledge. I'm, like I said, this much brain, regular brain this much. I might be wrong. But that's how it's working. So graph databases are excellent examples if you want to look at how to build a reasoner. Some of the most robust ones are there. Yeah, go ahead.
One more point is that, like, if you just have a dependency, like if you do pip install and it has to resolve a dependency graph, that's like a one-way relationship, and it's already a sound problem. Like it's already hugely complex. So to have arbitrary relationships going in all the ways, it seems like a very difficult problem.
Yeah, but like if you could define your bill of materials, if you could define your SBOM as an ontology, I think it would be easier to reason. I think that's that's a really good use case for the enterprise. Security teams, audits, pip install, checking dependencies. If your dependencies were defined as an ontology, I think it would be easier, right? But going back, so effectively what happened, my reasoner couldn't infer a property, so it ignored, that's how I've written the hydration code, it ignored the property that was not consistent, so the RDF never got the data, right? All of us all of us have access to this code. Why don't you try implementing it? It's not hard. It's like high school Python, right? You should be able to do it, right? But what it will do is give you an insight into the entire control flow of how this reasoner is picking up things and checking things, all right? This is a Sparkle query. Okay, syntax time. Don't ask me questions about syntax. Exactly 2 weeks or less, I'll have 2 really beautiful, big, beautiful notebooks for you. I didn't mean it. Look, I'm flying away from here like tomorrow, so.
Some of us aren't.
You can't deport me fast enough. All right. This is going on YouTube. Sorry. Okay. So effectively, this kind of suspiciously looks like SQL, right? It is SQL when you think about it, right? That's a name. It just starts with a question mark. Why does it start with a question mark? Because this is 20 years old. It shouldn't start with a question mark, right? So select a song and a performer where a song is, it's a song, belongs to the class song, and the song has a property which is performer, right? So you're going to get, where did I write it? So you're going to get all the songs and all the performers, right? Broke. Oh, I didn't run that one, sorry. Where's the helper function? There we go. Run this now. Yay! So we got all the songs and all the performers. 2 columns. Fairly straightforward. That's like select employee first name and last name from the table employees. That's what this is. Right? Fairly straightforward. What we just have to do is specify what each word means. That's this bit is what's confusing us a little bit, syntax-wise. Right? This is performed by is a word that derives its meaning from the music ontology that was defined earlier. That's all that's happening here, right? Otherwise, it's a fairly straightforward select statement, and that's all there is to Sparkle, right? But you can do really fun reasoning stuff. So, just give me a week or so. I'll have something really fantastic ready for you. I can give you a preview. In my work, what I have been able to do is, because consistently keep at it. So I have this thing, and what I've done here is collected as many analyses, patterns, design patterns types. That as I could. So you can see it's a path analysis, and this is the kind of Sparkle query pattern you'll use for it. And versus SQL, why would it not work in SQL? So I think I have a little over 500 of these patterns now. It's pretty deep. Definition-based equivalence. I mean, look, even I can't name names. I'm really bad at it. But the descriptions are good, right? So this is stuff that I've been discovering when I've been going through different ontology engineering examples, right? So that's a Sparkle pattern, right? So I'll have this in a workshop implemented soonish. Give me maybe a week, Make sense? But till then, we can just look at like basic Sparkle here, right? So we have to count songs by genre. In a regular SQL query, what does that mean? Group by, thank you. So it's a count and a group by, right? It's the same here. So here's all the classes we have, just a refresher. And here's all the properties we have in our ontology. So what we will effectively, I should have let you read through these, but effectively there's a song and a genre, right? We're going to have to pick a genre and a song, group by the genre, count the number of songs in each genre. Make sense? This is not hard at all. But how will we connect the song and the genre? In a database, that's a join. In Sparkle or in ontologies, we don't have a join. We don't need a join. It's already computed for us. It was computed when the graph was being hydrated. Why? Because we already have a property which has genre. Come on, check it out. So every song has a genre. We can just that's the link name. That's the link type. Right? So we can just go select genre, count the song, and store it in a variable count, where song is of the type song, right? And song has genre, some genre. Then we group by genre, then we order descending. How hard is this? Somebody's got to raise his hand and say, this is hard. No. Come on. Evidence that this is like really simple stuff and we've not been using it. Right? It blows my mind that, nobody talks about it anymore. And I'm trying to undead a Dracula here. This is really simple and elegant stuff, right? So here we go. And this is where I'm going to just format the results, right? Sparkle, if you remember the music question, where you said, when I'm printing the album, why does it say music.album? Now Sparkle will have to go to the object for which everything else is a property, right? So it's going to go to the default world and reason within that world. So you always have to give it a world before you query it, right? So we say default world.sparkle, and then we just run the query, right? So there we go. And here we have a result. Check this out. This is a group by. Try to run it in Spark. There's going to be at least 10 tutorials on GitHub that are going to say how to optimize group by in Spark. This is already pre-computed, right? It took us, milliseconds to get this data. Collaborative songs. This is, if you remember, I don't know how, there was a time back in the day when Facebook had no ads and it was actually cool. And my mom was not on Facebook and all my friends were there on Facebook, right? Then there was an announcement that Mark Zuckerberg made that, hey, we have network search on Facebook. And a lot of engineers said, wow, that is really cool, because you can't do it at scale. You could not search earlier in any social network, Shaurya and Shaurya's friends. You can do that. Facebook said, we can now do that, and you could do friends of Shaurya. How do you think that was working? This is, I don't know, when was Facebook invented? 2011, 2012, thereabouts. How do you think that was working behind the scenes? This is how. They just had a really large RDF graph that you can just query. Go ahead, sir.
Based on your experience, why do you think this has not caught on?
Oh, because it doesn't have a good name. It's like ontology. What? what's an ontology? Like, as evidence in this room, this is like really cool stuff, and I'm sure you'll agree it's cool, but I don't know. Why did they call it ontology? Could they not like call it something else?
I mean, it's not dead, right? Like
No, it's not dead. It's
link ML.
everything works through it.
going
Yeah.
on, And then in science, it's used maybe more at like the lab level rather than like the entire, you know.
Yeah, it is extensively used, especially in medical science. It is extensively used, but what's happened is the entire tool chain is stale. The entire tool chain is like 4 years behind the cutting edge, at least, right? It's incredible. We should have had a distributed GPU-based reasoning engine available to us yesterday. Instead, we're using an engine that was created like 12 years ago, right? We have all the algorithms in place. We have all the research in place. We have sample implementations in place. What we don't have is a reasoner that was from Python 2 to Python 3 converted. It's that. So I don't know. My guess is as good as yours. I'm zeroing in on the name because it's funny, but I don't have a real reason, right, as to why ontologies didn't catch on and why they sort of, but they are catching on, by the way. The agentic stuff you do, the large language models you do, the reasoning that we pretend is there in a large language model is all ontological reasoning. You'll see there's now suddenly like an uptick in the books on OWL and ontologies coming out right now. So go ahead, sir.
Your previous query, is there a way to make it sort by genre?
Sort by?
Yeah, so when you define the query in the cell above, where you have order by description, count.
I'll have to look for the syntax.
What's that?
I'll have to look for the syntax. Of course there is, but I'll have to look for
Because
this.
when I've been trying to put genre in there, it changes the ordering, but it's not sorting.
Yeah, it's not alphabetical. So I think there's a lexical order is a word. I don't remember which ontology has it. So I'll have to look for the syntax, but there's definitely a way to do that.
Okay, but it's not as simple as just putting genre in this case.
It should be, right? I agree.
Should be.
I agree. Sorry, you had a question, yeah.
Actually, one of
But that's a fantastic question, by the way. Sorry,
one
go
of
ahead.
the question or maybe insight is we have been using ontology forces us to define all the semantic relationship, but with large language model, we just feed the data into the model and it builds those relationship.
Yeah, why think when there's a brute force way to do it, right?
So that
No, so actually what you'll see, and this is my limited research, this is partially scientific because I've used this on small language models that I've built on my laptop, right? A language model actually generates a fairly good ontology in the first or second try. Why? Because it has absorbed the higher dimension semantics. So what's the dimensionality of any embedding in a language model right now? When I was tearing it apart, this is about a year ago, we were looking at 16,000 plus dimensions, 2 to the power 14. We're not talking about 2 dimensions, 3 dimensions. LLMs went the opposite way, right? We were in machine learning inventing algorithms for dimensionality reduction. LLMs said, keep increasing the dimensions till you start seeing some semblance of semantic clarity in the embeddings. So I think the most common one was 2 to the power 14, right? That's 16,000 some dimensions per embedding, per token. When you say the word Tokyo, it's represented as a string with 16,000 some terms by that number. It's a polynomial with that many terms. When you say the word camera, it's represented by that many. So LLMs, because of those embeddings that they've learned, and they've been trained on our human language, they're actually surprisingly, they're never consistent. That's a problem with LLMs everywhere. Right, we're pretending they're consistent, they're never consistent. Right, to the point that they'll generate things out of order. But LLMs are pretty good at it. So one thing we can do, one research that I'm still trying to work on, is if I go to an enterprise and I take all their data, all the emails, all the flyers, all the memos, all the attendance sheets, all the finance reports, whatever, and I train a small language model for them, will that model be able to give me a fairly accurate representation of that enterprise as an ontology? Because then I can reason about that enterprise. Then I can conduct an automatic audit. Then I can check for compliance, right? So this enables, we're going to pretend that we're using agents, but this is just standard Python code helping me analyze the existence of XYZ constraints in an enterprise, right? So unfortunately, I don't know enough people who would give me all the data of an enterprise, so I don't have that small language model yet. But I did try to fake data. So there's some measure of success there, but not completely. Did that answer your question? In fact, you could go to ChatGPT right now and say, build me a music ontology in N3 format, and my suspicion is that it's going to look very much, not identical, but like 80% there. So it's pretty effective. Make sense? Should we move on? I'm going to add a comment here because that was a fantastic question. Okay. We're still interested, right? I have like maybe half the notebook. How much time do we have, do you know?
Roughly 45 minutes.
Really? That's it? Oh, God, all right. I can study for 4 hours, too. Somebody show this to my son. I'm feeling really proud of myself. All right. Okay, so fairly straightforward. We're now looking at collaborative songs. This is interesting. We don't have a data CSV file called collaborative songs. If we go to music and we go to the data, we don't have something called collaborative songs. We just computed this new class. So this is pretty cool, right? We're going to say find collaborative songs, and we're going to say, hey, song has performed by one or more artists. No, sorry, more than one artists. That's a collaborative song, right? And when I do that, in a traditional database or in a traditional data engineering scenario, how do you think we'd do that? Do I hear a self-join coming? Yeah. Basically, you'd get into a management review where they'll say, why is this query taking so long? It's right there, right? This took milliseconds. The trade-off is storage, of course, right? But it's there. Storage is always cheaper than compute, I think, at least now, right? Come on, this is cool. It's really neat. We've not used any professional libraries yet. It's pure Python, and it's working as fast as like a big data tool, right? Albums and track counts. How do you think you'd do that in SQL? I'm writing pure Python code, so it'll take you a minute to read. But how would you do that in SQL? If I had to count the number of tracks in each album, if that data was an album, I just go group by album and count, right? But my album is in my songs database, right? So that's a tricky issue. Go ahead.
I was just going to say, join between albums and I guess maybe like a songs table.
Yeah, isn't it fun? Right? And now just try to say the other way around. You are Walmart, and I want to say invoices and orders, items and invoice. That's a join that's going to take ages, right? Let's see how long this takes. Oh, come on, no results. But it didn't take long. Let's find out why there are no results here, right? Let's look into this. We can debug it, come on, right? Maybe there are no songs or albums. So let's check that out. There are songs and there are albums. So then, what are the properties of a song? So it's got featured on. Yeah, I think featured on is the one. And similarly, on an album, we will have an inverse property, which would be, somebody read it for me, please. Oh, it's not. Okay, so we just connect through featured on. And either songs don't have featured on property defined in the data, again because of hydration problems, or featured on exists but it's empty. One of these two. So let's go look at that. We have 0 non-empty featured on. All the featured on properties in the data are empty right now. It would have taken the join just about this much time to compute, and we've even debugged our query, right? So we can rehydrate the data again. You know, we can fix this part because we just have to hydrate this one property. We can do that. Not a big deal, right? But hey, this is pretty cool, right? Would you agree? Somebody say yes.
Yes.
Thank you. Okay, and now we're looking at, let's define how we can extend this to say additional things about music, right? So what I'll do is now not use the RDF because that part's over. We'll define a new ontology really quickly, hydrate it with some examples, and run reasoning on it. This is sort of the meat and potatoes of this thing, right? We are building a very tiny reasoning engine in Jupyter Notebook right now on this data, right? So this is fairly straightforward, right? The only interesting thing is that RDF, we are borrowing the word song from it. We're extending our new song based on the song that we already have in the RDF that we import. Make sense? With me so far? All right. And now we have 3 new classes. We have a playlist, we have concert, and we have a music video. Right? Really specific vocabulary that we have now discovered for talking about music. Okay? Did I run this? I don't know. Let me run this. Okay, properties of a playlist. With, again, please ignore or please excuse me for repeating this again and again. I know it's an eyesore, but just for every cell I'm trying to set the context so I don't lose it, right? This is probably me being dumb. I'm sure there's a better way to write this code, right? Same deal. We're defining properties Again, why did we not define the properties inside the classes? Somebody want to say that again?
Because the property can belong to more than one class.
Anybody can use those properties. Any class can use those properties, right? So the properties are like a bag of words, right? So everything's equal there, right? Properties for concert. We're going to define additional properties for concert, as in we're talking language. We're not defining properties inside the concert class. We're defining them at the same level, right? So we're defining it inside the extended ontology, right? So let me just Control-Enter on both these things. And then for the music video, we're saying, hey, the music video was for some song, has a director, has a view count, right? Now, this idea of individuals. Individuals is every data point that was hydrated for any given class in the ontology. Make sense? Freddie Mercury is an individual. Bohemian Rhapsody is an individual, right? The music video for Bohemian Rhapsody is an individual. The concert where Queen played the song is an individual, and so on. So we'll create a playlist. I really don't know if this is arbitrary. Just don't hold me to these dates. This is where Hermit broke for me. Instead of me going in and fixing Hermit, I just created an alternative. So please ignore the ugliness here right now. Music video, connecting the three. What is connecting the three? Links. Bohemian video is a music video, has a director. Sorry, what am I reading? Queen performs at some concert. Road trip playlist contains the song. Can you see how it just computed properties? What you'd have to do is create foreign key relationships in our database, right? If you were doing this in the traditional sense, you'd have to create a primary foreign key relationship. Can you see that? Right now, I just computed joins between two tables. No sweat. Right? And you can just run this in a for loop, and you can just ingest all the data from a CSV file, and it's computing your joins as each record gets ingested. Right? So we're not computing joins at compute time. We're just doing it at data ingestion. Right? So here's all the properties, and here's my instances. Make sense? This is the coolest part, and it's slightly coffee heavy, right? Do you want to take 2 minutes, or should I just muscle through this? Somebody say.
Can I ask a question first?
Sure, go ahead.
I'm trying to wrap my head around this. And what's the difference here when moving from a more traditional framework where we might be using SQL for doing or whatever it may be, and using this ontology framework instead? How is this not just abstracting that work and abstracting that compute time somewhere else?
You're right. Yeah, you're right. So there's no magic behind it. I completely agree. So the trade-off is we could do this in real time. We could just compute stuff off of data, and we can still do that. Even in ontologies, the reasoner can be built to reason at search time, at the time when the user actually runs the query, right? The way I wrote the reasoner was that it would reason while persisting the data, right? This is how caching works, doesn't it? What we try to do to speed things up is say, hey, there's a database query, why don't you cache the results? So when it runs again, we'll pick it up from the cache. I just dragged the cache all the way back to when the database was running its, DML. when the database was ingesting data, this is nothing but a cache, right? I mean, it's the cached join that we just computed, right? So go ahead, sir. Sorry, let him finish. Yeah, go ahead.
So it's missing data engineering principles if we know that we're going to need some information. We generate that cache before you need it, not runtime.
Yeah, why not? Completely, yeah. So let me...
Format, then like create this whole new framework to think about how your data fits together.
Right, no, I agree. So the question is that, well, if it's just a matter of when do you cache something, why can't you use a regular framework and just, cache early? And you can absolutely do that, right? What we're limiting ourselves to right now is a bias where we're saying just this query and not every possibility that needs reasoning, right? So if this is all we're solving, you're right. But we don't know in the world what kind of problems we'll encounter. If there's like I have for kicks for the last 5 minutes of the workshop, I wanted to show I've built an ontology for Star Wars, right? So you can just like check it out and whatever reasoning I could get, I just dumped the script of Star Wars, the first 3 episodes, and into an LLM, and I said, okay, give me all the events. So, lazy, but I have the events data. Now that I have the events data, can I reason about it? So, I tried to build it, kind of works. Let's see. But I don't have it in RDF or Sparkle or anything like that, right? So the thing is that depending upon the context, you can always choose something. You had a question, sir. I'm sorry, I ignored you.
Yeah, I was kind of following up on this question, but tying back to something we said previously about storage is always cheaper than computation. Is it accurate to say, I'm also trying to wrap my head around the value impact here. Is it accurate to say that the trade-off here is not so much of storage versus computation, but memory versus computation?
It is, yeah, right now, till now, the trade-offs have been basically compute versus memory. Compute, memory, compute, storage, right? Now, when we see reasoning happen, you'll start seeing more interesting things come up, right? So there's this notion of restrictions, right? It's just the word they use, right? But it's basically what kind of rules we can write about the vocabulary that we have, all right? So let me just revise everything so that I have all these classes ready for us to review. There we go. These are all the classes. If you remember, this is the original one. We invented collaborative song, and then these are like additional classes we computed, right? This is in the extended ontology where we computed the playlist, concert, music video. And now we'll say existential restrictions, which look like the word sum, right? So if I want to create a new data set, again, can you do this by caching? Right? This is one example where I think it would be interesting to think about trade-offs between caching and this thing. Can we now invent a new category or a class that says award-winning artists? Right? Artists who have won some award. We can also say at least one award, but some is more semantically relevant here, right? So it literally is there as an operation inside already. So we can say, hey, a class that is award-winning artists is equivalent to, this is just a variable name that I'm using, a list. And in that list, how am I filtering my triplets? I'm filtering by saying Music ontology has one award. So there's an artist who has one award, some award from the award class. Straightforward-ish. Make sense? All right. Collaborative artist. More than one artist for a song. Right? Label artist. Signed to some label. We know that this is doomed to fail. Right? Okay. We're just creating classes right now. We're not actually running any code. This is just a list comprehension when you think about it. Right? You can recognize the list comprehension here, right? Similarly, cardinality restrictions. We've seen this in database, right? One-to-one, many-to-one, many-to-many, so on and so forth, right? So we can say solo song has exactly one artist. So there's exactly here, there's min here, there's max here. That's what those relationships look like, right? So you can see exactly, can you spot how I'm specifying the relationships? This is Python list comprehension. It's not even like complicated math stuff, right? Then universal restrictions. I don't think I implemented this completely, and so we can skip it, but I think there was a question somewhere earlier in the session where we said, hey, what if we keep coming up with, I think it's the manager-employee question, right? Right, so something like that, right? So we have rock song and rock only album. This is a kind of album that did not exist earlier. So we can have an employee who manages as a different kind of employee. So we were able to reason about employees, but then a manager becomes like a rock album, which is a different kind of a special kind of an employee. It's still an employee, but it has some additional things in it, right? I don't know, did that question, now can you relate to the...
Yes, I think the general question was, can two nodes have two separate relationships? And I think the answer is, if you make node A have a subclass, node A prime, and then you have a separate relationship with that.
Yeah, so the problem with that thinking is we're thinking in algebra, and we have to think in semantics. So we're engineers, our nature, biologically, we're geared towards the how. We have to bring us back from a how to the what, all right? So I'm sorry I didn't implement this. This is where the dichotomy, right? So I can either go ahead and now create a new genre, and then everything else under that genre, or I can extend something, and so there are multiple ways of doing this, and so I said, why get into it? So there is no rock genre defined yet. We just have a genre with a property somewhere, right? And then has genre, some rock genre. So one song can have multiple genres and so on and so forth. So this is just, right? Similarly, value restrictions, it must have this value, right? The birthday, you must be above 18 years of age. You must be XYZ qualifiers, right? You must be at least 5 years in the company before we think about gratuity or some other payment schedule for you. So value restrictions, fairly common. And then we can combine these restrictions, and this is so cool because it's kind of like writing if-else grammar. This is, you could imagine running like a 100-line rule, which is a complex mishmash of all the restrictions we've written before, right? And there we go. We can actually use complex restrictions, right? So we're saying, hey, an established solo artist, right? That's an artist who has won some award, so the award-winning artist, and collaborates with nobody else. Right? So that's a sum restriction, that's a value restriction. Make sense? So we can just keep inventing new semantics on the same data. Right? How many times have we had this situation where you say, who are my preferred suppliers? Who are the closest suppliers? Supply chain, right? Who are the preferred customers? Which ones are my key accounts? I know Salesforce people run that query every day and it takes like 3 minutes. And it's the difference between life and death on the 30th of every month. Right? We can keep inventing new semantics every day for our business. The Staples store in Tacoma, the best-selling pens in Staples, Tacoma, versus the best-selling pens in Staples, Arizona, Phoenix, Arizona, something like that, right? These can be really specific categories of the same data with no extra effort, right? We just keep defining additional semantics and keep playing with them, because all of us know by the time we come up with a product, there are emergent requirements. We can address it here very easily. There is a use case, again, from the COVID times, if I remember correctly, where they said, we suddenly, all of us got work from home, right? So they had to say meeting and then a remote meeting, right? This is peak COVID. We're not meeting in the offices. The folks who were using that ontology could start accounting for remote meetings like that. For everybody else, they had to insert a parameter in their database, a new column, remote Y or N. Right? So suddenly for important meeting like legal meetings, you could start recording data as remote meetings with like 0 changes to your database. Make sense? So complex. Now let's see how we use those restrictions. We've just modeled additional classes. We do have time, right? I'm panicking a little bit. We do have time, right? Okay. So now we run this part. Okay. Music onto artists. So, I'm just creating sample data. Look at me panic. We'll set up some relationships, because the moment we set up relationships, we will be able to compute our extended classes, right? So, excuse me. And yeah, let's compute. So we know that Road Trip is a playlist, Wembley is a concert, Bohemian Rhapsody is a music video, Collaborative Artist is an artist, Test Award is an award, and so on and so forth. So we know that the class hierarchy is working for us, right? Yeah, let's just run it. I'm pretty sure some of your laptops will fail on this one. I say a little prayer each time I run it. That's how generally it works. Nothing. So if it says nothing, means everything's fine, right? So sync reasoner hermit is basically saying send my ontology into hermit, the reasoner, and let it go through my data to check for consistencies. That's all it's happening, right? And yeah, let's see the restriction classes. Let's check against those and see if there was any restriction that came up. Nothing. This is actually erroneous. We created that data. We know there are these classes that belong to restrictions. We have created an artist called collaborative artist for specifically that reason. I don't know how to fix Hermit. Maybe my code is bad. I'm like really impatient, right? If you check Hermit, you know, you can reminisce, oh, the internet used to look like that once upon a time. You literally can't reminisce about when you look at the Hermit. Those were the days. Check that out. Once upon a time, we used to have these websites with like when Twitter had still not given us, or Bootstrap had not been invented, and so on. You know, that download button. So yeah, so I don't know. I don't have any patience for this. So let's DIY the reasoner here. All right, this is super cool. How hard could this be? Like, it's not like writing a compiler. It's not even writing a SQL engine, right? It's just literally this. So I think the function is a little big, but I'll explain each one of these things to you. So effectively, the way a reasoner is going to work, it's going to have a list of all the rules that we defined, right? And it's going to just pick the piece of data and just run it through the rules, right? It's not that hard. I think it's called the RETE, RETE algorithm. It's a fairly straightforward thing, and you'll see that there's more comments here than actual code, right? So it's not a big thing. So we're saying go through every individual, go through every instance in our ontology, just check for a name. If it doesn't have a name, or if it doesn't have a defined name, we don't need to reason about it because our data has missing pieces, so we don't want to break the function for those, right? We'll just take, and now we'll create a list which is just manual types. We're going to capture every class that we created, every new data type that we created here for that individual, right? So we'll check for the award-winning artist. How do you think we do that? We just say, is the instance of an artist and has the attribute, has one award. So, you know, literally what we were defining for the class here, we're just implementing it, right? And we're adding it to the award-winning artist type. And so on, we check for collaborative artist, we check for labeled artist, we check for solo song, and look, it's an if statement. I mean, how hard can this be? Right? And if we say a solo artist should be, look, I just took one individual whose name is solo artist, should be an award-winning artist, collaborative artist, label artist. Collaborative artist should be a collaborative artist. Solo song 1 should be a solo song. Collab song is a multi-artist song. We just reasoned through our data, the same data set, and we could actually bring out more semantics. Does that make sense? So I'll close this with some like theory and some intuition. We're not looking at code anymore. But the traditional approach, you'll have to explicitly state every fact for every instance of data, right? You're going to have to say award-winning in the type column again and again. We didn't do that here. We just defined a rule. Award-winning is where the number of awards are more than 1, right? 1 or more than 0, I don't know. But we just defined a rule. We did not actually create a new column in our database to say type something, right? You'll always have to manually maintain all this data. This is why they invented transactions, right? Lock the database, transactions are running. You take something out of your account, it will only reflect in my account tomorrow once the bank has done the tallying and everything, right? So you don't have to do that anymore. If the artist wins a new award, our relationships hold, right? The logic continues to work. As your data state changes for different individuals, stuff continues to work. Make sense? Lost? No? Yes? Because we have a set of rules by which to reason about the world, it doesn't matter how much data there is in the world. As the data in the world changes, our rules can keep assessing the new data. Make sense? This is what, in the model view controller world, the controllers were built for, and nobody used them. Right? Ontology-driven approach, you just define the rule, and you assert the fact. And the reasoner, like we built a really dumb Python reasoner, we literally said if, right? So there's no parser in the reasoner that will parse the rule and then implement it. So if I was building an N3 reasoner, for example, I should be able to parse the N3 language and then, put up a Python function against it, right? So, but right now, just the if-else, it applies the logic, right? I want to say automated, but everywhere in literature you'll hear intelligent, right? It will automatically discover new data points. As more artists win awards, your award-winning artists bucket will always have the latest data. What do you have to do to update that data? You just have to say select award-winning artists. That's it. Does that make sense? Lost? I'll show this to you again, okay? I have defined an award-winning artist as somebody who has won some award. Some award, right? In my life, every year, a new, let's say, Grammys happen, right? Different artists continue to win awards. One approach is every time an artist wins an award, I go and update my database table. That's what we're doing today. I go and add the award into their column. Or I go add a foreign key to the awards table or something like that, right? Here I did nothing, just more data got added to my artist table, all right? And then when I'm executing that, award-winning artist, the reasoner just runs an if statement before giving me the data, right? And if the individual has won an award, some award, it says here's the award-winning artists. So effectively what I did here was, and this is where the compute and cache question comes up again, effectively what I did here was write group by awards count greater than 1. Greater than 0, right? But I did that in a semantic manner, right? So when I run my reasoner, it just gives me all the award-winning artists. I don't have to go and update the database, or I don't have to do anything else. It kind of looks like science fiction. It's not. It's slightly roundabout, and so give it let it marinate.
But if you
for a coffee,
using a general reasoner, you wouldn't even have to write a new. I mean, there you wrote a new pattern match, right?
Yeah. You don't have to. You're right. Absolutely. You just define your semantics, and the reasoner does it. Yeah. Go ahead.
So, right below that, it says that the first bullet on 2 is if artist loses awards, they're automatically reclassified.
Yeah.
But your rule is just checking.
Some award.
Yeah, but it's not say. So what it? If some award make them a.
So it works
Oh,
both.
so if your word's taken away,
Yeah. Then my artist is no longer an award-winning artist.
okay.
Isn't that cool? Yeah. Yeah, just about like the moment you're about to sleep and you're like, oh, that's what it's doing. You know, at least with me, that's how. So yeah, so we always have consistency. We actually don't have to rely on modifying database tables and locking database tables for transactions or duplicating database tables and then running analytics on top of the duplicate, database replica. We don't have to do any of that. It's always consistent. It's always reasoned through. That's not a bad idea when you think about mission-critical applications. It's not a bad idea. This is a Palantir thing. Don't tell them I told you this. But like a typical black box is going to have terabytes of data. Terabytes. A typical airplane black box is going to have terabytes of data, right? Try querying it. Nah. But what if you could reason through it? Right? So the whole point is we can reason through consistency, like in a consistent manner. We are not dependent on you did the filters before you joined, but you joined before you filtered. Right? Why are we consistent? Because we're focused on one word, and that word is what? We're focused on what do we want, and we don't care how it's done. The how is the reasoners implemented, or we can do something simple on our own. Make sense? Knowledge reuse I would use with caution, because we're mixing ontologies whenever we're reusing knowledge. But it's done quite often, actually, surprisingly often. Right? So you define the rules, you add some data, you run the reasoner, you get the results. Basically a 4-step process. Make sense? The manual approach used to be add 2 Beals to the artist table, add collaborations to the collaboration table. Remember to add artists to the collaborative artists table as well. When you're hydrating, when you're adding data in your database, you'd basically do all these writes in your database. Right? Remember to update the change, write application code to maintain consistency. Now, you define this rule. You don't actually change your database code at all, and it just works. So effectively what they did was not technical. They did something that was just common sense. They said, what are we trying to achieve? Let's figure out a framework to extract that away from the how of the problem. Right? So all the mechanics of how database queries work, this, that, and the other, became the how, and the what became the semantics in the ontology. Make sense? This is the serialization part. This is what the ontology manager application code is also doing. So it's effectively going to put in, just ontology.save, and it just creates a file for you. So if you run it, it will automatically right now create these files for you. I did not cover Turtle and RDF, but I have a quick notebook ready for that as well. We can look at that if you want. That's it. Remember to destroy and clean up your ontologies, because computers still have finite memory. 2025 and we still don't have infinite memory computers. So we'll have to periodically clean up. It's more important to clean up for semantic reasons, because ontologies that are no longer relevant, that are stale, need to be sort of groomed out of the system. Right? Use cases keep emerging, new things keep evolving, old definitions die, so we have to keep ontologies updated, right? That's it. JSON LD. my favorite, like currently, because JSON's a good idea. I think we can represent, although there are certain reasoning rules that are hard to do in JSON, but nothing broke. I tried JSON, works well. Yeah, that's the workshop I have. How much time do we have? Do we have 5 minutes? We don't have 5 minutes?
We have 1 minute.
Are you serious?
Yeah.
Can I show you pictures before we go? All right. Oh, let's close all this nonsense. Okay. Quickly. Of course. I told you at the start of the meeting, the links are broken and my brain is not working, seriously. Music, study, supply chain. All right. So here, at the bottom of this page, I have a simple flow of how the movie lens data reasoner is working. So remember we had all those recommendation engine type rules also built in. So this is how that thing is working. It's saying you load the data set, you normalize the CSVs. So some CSVs may have 1.0, 2.0, ratings may have decimals, which will be loaded as strings, or IDs may be integers, which will be loaded as strings, and so on and so forth. So you normalize all that, and then you create your entities, right? And then you validate the relationships, you clean the invalid data, and then you apply the reasoning rules. And, we create the enriched entities, the recommendation entities, the cross tastes. I don't remember the class that I created that. But we just basically create that goes into a pipeline, and we basically have recommendations, cross-genre. We basically have recommendations. Fairly straightforward, not too complicated, right? Let's do this one more time. And here's the beauty of it. The more you do it, the better you can refine it. I did a slightly better job here. When we now look at the framework, it's not that complicated. It's a fairly straightforward thing happening. It's still the same stages. It's still the same stages, but it's slightly cleaner than what was going on here. Right? Let's try this again. This is a supply chain ontology. I think, I may be wrong, but if you had to write a custom reasoner for a custom ontology, I think we have a good framework, which is, I hope I put it here, which is this. 4 phases and we're done. We start with, oh, this is what I don't like. We start with data ingestion. We provide ontological processing. That's where all the validation rules come in. We provide analytics. This is where the new classes and the rules come in. And we basically just output. 4 steps. So, and these are like literally method names. So you can actually go in and say, check relationship integrity is a method you can implement. So you can just use this thing as a class, as an interface to your reasoner class, and you can just implement reasoner for any ontology. So what this is how general purpose reasoners work. All we're doing is implementing this interface on my ontology and building my own reasoner. It took me 3 iterations, but it works. It actually works because I'll show you for the 4th ontology, it's probably the same. Actually, I didn't add it, I don't know. Don't work late at night. You forget what you were doing. Yeah, I think I didn't add it. No. But the reasoner works. I'll show you something here. Yeah. What I did here was I can add new data using the reasoner. So I'm creating policies here, right? And I can update my database through my reasoner. So my database only gets updated when this data gets validated first, right? So I validate my data and then it appends to the database. Ever wrote a data validation part to a web service before? It's like, nails on a chalkboard, right? Here all we did was, how did the validations change from use case A to use case B? I just defined in the ontology. I didn't actually touch anything in the code. I didn't touch any one iota of the database code, right? So effectively, it's the reasoner built on the same framework. I think this is the last time I captured it. So sorry, I just wanted to show you boxes before we leave. Right. That's the big thing I wanted to show you, Star Wars. Oh, do we not have Star Wars? Come on. We do have Star Wars. We also have Lord of the Rings. I don't know what I'm doing. Oh, by the way, that's the Star Wars ontology. Don't ask me how this comes out. I happily watched, not happily, I have a love-hate relationship with Star Wars. When alone, I don't like those movies, but when with friends, I like them. Don't tell them I said that. But I have an IPyNB. Yeah. So I could reason through the Star Wars data to get you this. That's the character network for episode 4, 5, and 6. Right? That's who are not connected too many times. Guess who this guy is? Do you want to guess who this big circle is? It's connected to lots of people. Star Wars. Yeah, of course. And this is based on data. I'm not saying it because I saw the movie. This is character appearances. So check out. Luke Skywalker appears pretty consistently through each movie, but it has a break in episode 2. I didn't know that. I didn't remember it. Right? Did you know that the most amount of conversations Leia had, and goes to how we treat women in the industry, as if I'm one of the big producers in Hollywood, is actually with Chewbacca. Not joking, this is the data talking right now. That's the character networks for each of the episodes. I really like the graphic, sort of like a triptych feel to it. That's character affiliations. So the Rebel Alliance actually had the most number of people in it. I don't know why they were scared of anything. That's relationship types. So I don't remember what, but I remember there was a radar graph that I wanted to show you. Oh, that's in Lord of the Rings, yeah. Yeah, that's battles by scale. I think the biggest battle was unknown. That's the ship analysis. I just run Star Wars into the ground, give it to an accountant, and make him write numbers against it, right? So it's just, that's appearances and classes of ships in the Star Wars trilogy. And that's, of course, locations. So a lot of episode 1 actually happens on Death Star. And then Jabba's place and Ewok village, and I don't know, what is that? Home 1. And LLM found these nouns. I didn't do anything. I just gave it the script and it just, right? So location frequency, Death Star, and then Millennium Falcon. Millennium Falcon doesn't feature as much in episode 1. I didn't remember that, and barely features in episode 3. I didn't know that either. So, yeah, may the force be with you. That's all I have. Thank you.
So did you say you generated the Star Wars data with like ChatGPT or something?
Yeah, I just gave it the PDF, the script, and I said just, okay, get me all the events in chronological order. And now I have the events. From that event, I can say, get me all the nouns. Now I have all my nouns. Get me all the verbs. Now I have all my relationships. I have my ontology.
So if that's the case, could we use ontologies as almost a way to make large language models safe, or to like?
That's exactly, a lot of work is going on in that department. I'm sorry, for the larger room, he's saying, can we use ontologies to make language models safer? And the answer is absolutely yes. There's evidence on the screen. I mean, it's entertaining evidence, but it's there. Right? So I hope this was interesting. I know people have left. But yeah, let's build the next generation of these tools. And thank you so much, everybody.